Hello there and welcome to Science for Sleep. Where curiosity gets cozy, the universe lowers its voice a little, and even the strangest stars are allowed to be strange at a comfortable pace. Tonight, we are drifting toward one of the oddest points of light in the known sky, a star so unusual that astronomers have been looking at it for decades and still have to admit, with admirable honesty, that something about it does not fit neatly into the usual boxes. Its name is Przybylski's star, which is already a small challenge before the science even begins. If you tried to say it out loud and quietly negotiated with the consonants, you're not alone. It is also known by the much less dramatic name HD 101065, which sounds like a catalogue number someone might put on a drawer full of spare telescope parts. But behind that plain label is a star with a spectrum so peculiar, so full of rare chemical signatures, that it has become one of those objects astronomers mention when they want to remind themselves that the universe still has a sense of humour. And before we float too far into Centaurus, where this strange star waits in the southern sky, I would love to know where you are listening from tonight. Are you somewhere under a bright city glow, where only the strongest stars push through the haze? Are you somewhere quiet, where the night sky has room to breathe? Or are you listening in the daytime, letting a star nobody can explain keep you company, while the ordinary world goes on around you? It is a lovely thing, really, that a star more than 300 light years away can become part of your evening, your morning, or your little pocket of rest. So if you find this journey soothing, interesting, or just a calm way to let the mind loosen its grip on the day, I would be grateful if you gave the video a like and maybe subscribed. It helps this quiet corner of space reach other people who might also enjoy learning about mysterious stars at a speed that will not frighten the pillows. Now, settle in, let your shoulders drop, and imagine the sky as a great dark page. Most stars on that page are not really mysterious in the dramatic sense. They may be enormous, violent, ancient, or beautifully complex, but for the most part, astronomers understand the broad rules. A star is born from gas, it shines by fusion, it spends its life balancing gravity and pressure, and eventually it changes, collapses, expands, fades, or explodes, depending on how massive it was to begin with. There are many details, of course, and science is very fond of details. Stars have temperatures, masses, ages, magnetic fields, atmospheres, rotation speeds, pulsations, chemical fingerprints, and occasionally habits that make researchers reach for a second cup of coffee. But overall, stars belong to families: red dwarfs, yellow dwarfs, blue giants, white dwarfs, neutron stars, variable stars, binary stars, chemically peculiar stars. The sky is not random. It has categories, it has patterns, it has a kind of order. Przybylski's star is uncomfortable inside that order, not completely outside it, to be fair. It is not a ghost star, it is not a tear in space, it is not a machine, and it is not evidence that someone has been seasoning the cosmos with exotic elements for artistic purposes, tempting as that phrase may be on the internet. It is a real star, observed with real instruments, studied in real papers, and placed in a real class of stars known as AP stars. These are chemically peculiar A-type stars, stars whose outer layers can show strange abundances of certain elements. They often have strong magnetic fields. They can rotate slowly. Their atmospheres can behave like quiet sorting machines, allowing some elements to sink while others rise and gather in patches. If a normal star's atmosphere is a stirred soup, an AP star's atmosphere can be more like a carefully layered dessert that no one remembers ordering. So yes, there is a framework for thinking about it. But Przybylski's star takes that framework and politely bends it until it makes a creaking noise. The mystery begins with light. This is often how astronomy begins, because for most stars, light is all we have. We cannot visit them. We cannot scoop up a sample from their surface. We cannot knock gently and ask if they might explain themselves. Instead, astronomers collect starlight and spread it out into a spectrum, separating it into its colours the way a prism turns sunlight into a rainbow. But a stellar spectrum is not just pretty, it is information. Hidden inside it are dark and bright lines, tiny interruptions made by atoms and ions absorbing or emitting particular wavelengths. Every chemical element leaves its own pattern, like a barcode, or a musical chord, or a set of fingerprints left in light. Hydrogen has its marks, calcium has its marks, iron, nickel, oxygen, carbon, sodium, magnesium, each one has a way of saying, I was here. Most stars show familiar ingredients. Hydrogen and helium dominate, because the universe made a great deal of those early on and has been using them ever since. Heavier elements appear too, especially in the outer layers, but usually in amounts that make sense for the type of star and its history. When astronomers looked at Przybylski's star, however, the fingerprints did not behave. The usual iron lines were surprisingly weak. Some common elements seemed underrepresented, and then, scattered through the light like rare spices in a recipe that had escaped supervision, came signs of elements that stars do not usually display so loudly. Strontium, neodymium, praseodymium, holmium, yttrium. Lanthanides and other rare earth elements appeared in extraordinary abundance. The spectrum looked less like an ordinary star and more like the periodic table had quietly fallen into it during the night. That alone would make Przybylski's star fascinating. Rare earth elements are not magic despite their name. They are not necessarily rare in every context either, which is one of chemistry's little naming jokes. But in a stellar atmosphere, seeing them so strongly is strange. Some chemically peculiar stars do show enhanced rare earth elements, especially magnetic AP stars, and that has to do with how atoms move in the outer layers under the combined influence of gravity, radiation, and magnetic fields. Imagine sunlight from within the star pushing certain atoms upward, while gravity pulls them downward, and magnetic fields help arrange the motion into quiet, stubborn patterns. Over time, the surface can become chemically patchy, and very different from the star's overall composition. The star is not necessarily made entirely of these strange materials. Its atmosphere is simply displaying them with unusual enthusiasm, rather like someone wearing every badge they own on one coat. But the story does not stop with rare earth elements. That would be odd enough, and odd enough is usually plenty for one star. Przybylski's star has also been linked in various studies and debates with possible signs of elements that are radioactive and short-lived. Promethium, for example, has no stable isotopes. Technetium is also famous for being radioactive. Some researchers have reported or investigated possible lines from these elements in the star's spectrum. Others have revisited the same claims and warned that the lines are blended, uncertain, or not strong enough to prove what earlier interpretations suggested. This is where the mystery becomes especially delicate. In astronomy, a spectral line can be a clue, but it can also be a trap. When a star's spectrum is crowded with thousands of lines from many unusual elements, one feature can overlap another. It is a little like trying to identify a whisper in a room full of people quietly reading chemical names in different languages, so we have to be careful. Przybylski's star is not simply a star full of impossible elements, as it is sometimes described in more excited corners of the internet. The real situation is more interesting, and also more responsible. Astronomers see an extremely peculiar spectrum. They see rare earth elements in astonishing amounts. They see patterns that may include or hint at radioactive species, though some of those claims remain uncertain and debated. They see a magnetic, slowly rotating, pulsating star, whose atmosphere may be separating elements in ways that are difficult to model, and they see enough unanswered questions to keep returning to it, because science is not only about the moments when everything clicks. Sometimes science is about staring at the same strange light for years and saying, that is still not normal. There is something comforting in that, in a way. The universe is not required to be simple for us. It does not have to organize itself according to the convenience of human textbooks. A textbook is useful, of course, It is a map. But the sky is the territory, and the territory can always contain a valley the mapmaker did not expect. Przybylski's star is one of those valleys. It is not the brightest star in the sky. You will not glance up casually and have it leap out at you like Sirius or Venus pretending to be a star. It sits in the southern constellation Centaurus, too faint for unaided eyes under ordinary conditions, a quiet 8th magnitude object that requires help to see. It is not famous because it dominates the sky. It is famous because when we looked closely, the light coming from it seemed to have brought a puzzle. And what a puzzle it is! A star slightly hotter than the Sun, roughly in the range where A-type and F-type descriptions have been argued over, because its spectrum is so chemically tangled. A star with a magnetic field. A star whose brightness can pulsate in minutes, making it part of the rapidly oscillating P group. A star that may rotate so slowly that one turn could take far longer than a human lifetime, though the exact value is not simple and remains a matter of interpretation. A star whose atmosphere is so strange that even naming what kind of star it is becomes less straightforward than usual. Most stars allow us to introduce them politely. This is a red dwarf. This is a blue giant. This is a white dwarf. Przybylski's star seems to arrive at the door wearing an AP star name tag, carrying a bag of lanthanides and refusing to answer several basic questions until someone brings a much better spectrograph. The person whose name it carries, Antoni Przybylski, was a Polish-Australian astronomer who noticed its peculiar nature in the early 1960s. Imagine that moment for a second, not as a dramatic movie scene with thunder outside the observatory, but as the quieter kind of discovery science is often made of. A spectrum is examined. Something does not match. The lines are wrong. The classification does not settle. The expected signs are weak, and unfamiliar ones are strong. There is no explosion, no alarm bell, no glowing caption in the sky saying, "Important mystery begins here." There is just careful attention. A scientist looking at data and deciding not to force it into a familiar shape. That is one of the noblest little acts in science, really. To notice when something does not fit and instead of smoothing it away, to let it remain strange long enough to be understood. Since then, HD 101065 has become a kind of cosmic riddle passed from one generation of astronomers to the next. Each new instrument brings more detail. Each new analysis can sharpen one clue and blur another. The star has been studied with high-resolution spectroscopy, magnetic measurements, photometry, and models of stellar atmospheres. Some ideas have become more grounded, others remain speculative. Could the unusual abundances come from atomic diffusion in a powerful magnetic field? Very likely, at least in broad terms. Could there be processes in the atmosphere that concentrate rare elements into layers or spots? That seems very plausible. Could some apparent radioactive signatures be misidentified because the spectrum is crowded and the atomic data are difficult? Also, yes. Could something more exotic be happening, such as the decay of super-heavy elements or unusual neutron processes near the surface? Those ideas have been explored, though they sit in the more speculative part of the room, probably near the snacks but not yet at the main table. And of course, because this is the modern world, whenever a star looks too strange, someone eventually whispers, "Aliens." It is almost a reflex now. A star dims oddly, perhaps aliens. A radio signal appears, perhaps aliens. A spectrum looks peculiar, perhaps aliens with a chemistry hobby. But the sensible approach is calmer. Extraordinary claims need extraordinary evidence, and Przybylski's star, while deeply odd, does not require us to leap straight to artificial explanations. The universe has many ways to be weird naturally. Magnetic fields can sort atoms, stellar atmospheres can stratify, spectral lines can blend, rare elements can appear prominent even when the whole star is not made of them. Nature has a very large toolbox, and it has been using it for much longer than we have been trying to label the drawers. Still, the fact that we should be cautious does not make the star less wonderful. If anything, it makes it more wonderful. A mystery that survives careful skepticism is more satisfying than one that depends on exaggeration. Przybylski's star does not need to be a beacon, a laboratory, or a message to be remarkable. It is enough that it is a real star whose outer layers seem to have arranged the periodic table in a way that keeps experts busy. It is enough that its light, after travelling for centuries across space, arrives at our telescopes carrying the marks of elements we rarely expect to see so clearly in a star like this. It is enough that when we ask, what exactly is happening there? The honest answer is still, we have several ideas but not the whole story. That honesty is one of the softest and strongest parts of science. We often imagine science as a collection of answers, and yes, answers are important. They let us build spacecraft, predict eclipses, understand diseases, make clocks, cook dinner without too much guesswork, and occasionally explain why your phone knows where you are more accurately than you know where your keys are. But science is also a way of keeping questions alive without turning them into superstition. It lets us say, I do not know yet, and then reach for better measurements. It lets us be curious without being careless. Przybylski's star is a beautiful example of that. It sits there, not demanding belief, not offering a simple story, just shining with its strange chemical signature, while astronomers try to understand what its atmosphere is doing. So tonight, as we begin, we are not racing toward a single neat explanation. We are going to take the scenic route because this star deserves it. We will begin with where it is and how it first came to attention. We will look at why a star's spectrum is like a message written in light, and why this particular message looks so difficult to translate. We will wander through rare Earth elements, magnetic fields, slow rotation, pulsing starlight, and the careful debate over radioactive elements that should not be casually placed in a stellar atmosphere without asking several follow-up questions. We will keep our feet on the ground, scientifically speaking, even while our imagination drifts a few hundred light years away. That is usually the best arrangement for bedtime astronomy. The mind can travel, the body can stay warm. Perhaps what makes Przybylski's star so compelling is that it reminds us how much of the universe is known through indirect evidence. We do not see the star as a solid thing we can touch. We see its light. We read its lines. We infer its chemistry, temperature, motion, magnetic behaviour, and pulsation from signals that have crossed interstellar space. That is astonishing when you pause with it. A faint star in Centaurus sends light outward. Some of that light reaches Earth. A telescope gathers it. An instrument spreads it into a spectrum. A person, or now a computer guided by people, compares the patterns with laboratory measurements of atoms. From that, we begin to speak about rare elements, stellar atmospheres, and physics happening in a place no human will ever visit. Astronomy is not only looking up, it is listening carefully to light, and maybe that is a good way to settle into this story. Not with the idea that we are about to solve the unsolved all at once, but with the quieter pleasure of learning how the mystery was found. There is a special feeling in meeting a strange object properly, before the theories, before the debates, before the dramatic claims and the cautious corrections. There is the star itself, a small point in the southern sky, too faint for casual attention, ordinary looking until its light is opened, patient, distant, turning slowly, perhaps incredibly slowly, beneath a magnetic field that helps make its atmosphere unlike almost any other we know. It has been shining all this time, not for us, not at us, but simply because it is a star. We're the ones who noticed the oddness. Now, if we begin not with the chemistry, not with the strange elements, not with the magnetic field or the slow turning that seems almost too patient for a star, but simply with the sky, Przybylski's star looks almost shy. That may be the most surprising thing about it at first. For an object that has earned a title like the star nobody can explain, you might expect something dramatic. You might imagine a bright blue spark that catches the eye immediately, or a red ember pulsing in a way that makes even casual stargazers stop and say, "That one is definitely up to something." But the real star does not do that. It does not dominate the night. It does not announce itself from the heavens like a lighthouse with a secret. It sits quietly in the southern constellation Centaurus, too faint for the unaided human eye under normal skies, tucked among countless other points of light, looking from Earth like just another small star in a very crowded universe. If you passed over it with a beginner's telescope, you might not feel anything unusual at all. It would not wink at you. It would not glow green. It would not rearrange itself into a helpful arrow. The universe, as usual, does not label the strangest things for our convenience. Centaurus itself is already a grand piece of sky. For many people in the northern hemisphere, it feels distant and almost mythical, because much of it belongs to the southern night. It is one of those constellations that reminds us how local our own view of the cosmos really is. The sky above you depends on where you stand. Someone in London, Toronto, or Berlin may know Orion and the Big Dipper, like familiar furniture in a dark room, while someone in Australia, Chile, or South Africa may look up and see Centaurus climbing confidently overhead, along with the Southern Cross nearby, and the bright stars Alpha Centauri and Beta Centauri making that part of the sky feel busy and alive. Alpha Centauri, of course, gets most of the attention, because it is our nearest neighbouring star system, and astronomy, like humanity, can be very fond of whoever lives next door. But Centaurus contains more than famous neighbours. It contains star clusters, dark clouds, brilliant stars and hidden oddities. Somewhere within that broad southern pattern sits HD 101065, a faint point that seems, at first glance, to have no reason to trouble anyone's sleep. That is one of the gentle lessons of this story. The strangest star in a region is not always the brightest. Brightness is not the same as importance. A star can be visually modest and scientifically outrageous, rather like a quiet person at a dinner party who says very little for 2 hours and then casually reveals they have solved a mystery nobody else in the room understood. Przybylski's star is not a show-off in ordinary light. Its apparent magnitude is around 8, meaning it is below the limit of naked eye visibility for most people. The human eye, even under very dark conditions, usually reaches only down to about magnitude 6, give or take, depending on the observer, the sky, the weather, and whether someone nearby has just ruined your night vision with a phone screen. So this star needs optical help. A good pair of binoculars under dark skies might bring it into reach, and a small telescope can show it as a pale little point, but that point does not reveal its story by shape or colour alone. You have to ask the light a better question. This is where astronomy becomes beautifully indirect. When we look at the moon, we can see mountains and craters. When we look at Saturn, we can see the rings. When we look at Mars, we can see a reddish disk, sometimes with darker markings if the telescope and atmosphere are kind. But most stars are too far away to show surfaces. Even through powerful telescopes, they remain points, because distance compresses them into tiny signals. A star may be larger than the sun, hotter than the sun, older than human civilization by billions of years, and still appear in the eyepiece as a dot. It is a humbling arrangement. The universe is very large, and our eyes are very small, which is probably why we invented instruments and then immediately began giving them complicated names. So, to understand a star like Przybylski's star, astronomers do not merely look at it. They take its light apart. They collect the starlight through a telescope and pass it through a spectrograph, an instrument that spreads the light into its component wavelengths. To the eye, this may look like a strip of colour. To an astronomer, it is more like a document. The colours are crossed by lines, some dark, some bright, each one connected to atoms and ions in the star's atmosphere. When light moves outward from the hotter inner layers of a star and passes through cooler gas above, atoms in that gas absorb very specific wavelengths. The missing pieces become absorption lines. These lines can reveal which elements are present, how hot the atmosphere is, how dense it may be, how the star is moving, whether it is rotating, whether it has a magnetic field, and sometimes whether different layers of the atmosphere are behaving in complicated ways. It is a strange kind of reading, not reading letters on paper, but reading absences in light. From Earth, HD 101065 is not terribly far by galactic standards. Roughly 3,500 light-years is not close in any human sense. It is not a weekend trip, unless your weekends involve bending physics into a shape that makes engineers nervous. Light itself takes centuries to cross that distance. When the light reaching our telescopes tonight left Przybylski's star, Earth was in a different human era. People had not built modern observatories, launched space telescopes, or argued online about spectral classifications. That beam of light travelled through quiet interstellar space while generations lived and died, cities changed, languages shifted, and eventually someone built instruments sensitive enough to notice that this modest star had a wildly unusual chemical signature. In the scale of the Milky Way, though, a few hundred light-years is still part of our neighbourhood. Our galaxy is about 100,000 light-years across, so this is not a mystery from the edge of creation. It is a strange neighbour, not next door but certainly on the same vast galactic street. That makes it even more interesting. Sometimes, when we think about cosmic mysteries, we imagine them far away, hidden in the early universe or buried near black holes at distances that make the mind give up and go make tea. But Przybylski's star is not an unreachable quasar from near the dawn of time. It's a star in our own Milky Way, in a recognisable constellation, close enough that Gaia and other surveys can measure its motion and distance with impressive precision. It belongs to our stellar neighbourhood, broadly speaking. It is part of the same galaxy as the Sun, formed from the same long history of gas clouds, supernova debris, gravity, and time. And yet, when we examine it closely, it does not behave like a star that read the basic instruction manual. From the outside, as a point of light, its first oddness is easy to miss. It is not violently variable in a way a casual observer would notice. It does not flare like a dramatic young red dwarf. It is not visibly surrounded by a nebula. It does not sit at the centre of an obvious disaster scene. It is just there, catalogued, numbered, measured, HD 101065, HIP 56709, V816 Centauri. Astronomers give stars many names, partly because different surveys and catalogues were built for different purposes, and partly because astronomy has been collecting sky objects for so long that the filing cabinet is now the size of civilization. The HD name comes from the Henry Draper catalogue, a major catalogue of stellar spectra. The HIP name comes from the Hipparcos mission, V816. Centauri is its variable star designation. Przybylski's star is the human name, the one attached to the astronomer who saw that something was deeply peculiar in its light. The name matters because it marks a moment of recognition. Before a star becomes a mystery, it is often just data. Coordinates, brightness, colour, a line in a catalogue. Then someone pays attention. Antoni Przybylski examined its spectrum in the early 1960s and found that it did not fit neatly into normal stellar classification. That phrase, "did not fit," sounds modest, but in science it can be the beginning of a very long story. Most stars can be sorted by temperature and spectral features into familiar categories. O stars are very hot and blue. B stars are still hot. As stars have strong hydrogen lines. F, G, K and M stars move gradually cooler and redder, with different features becoming important. The Sun is a G-type star, pleasingly ordinary in that respect, though we should not say that too loudly in front of it. But HD 101065 was difficult. Its spectrum was crowded with features that made normal classification awkward. Common markers appeared weak or confused. Rare earth elements appeared unusually strong. The star did not simply refuse one box. It seemed to lean over several boxes and rearrange the labels. The setting in Centaurus adds a quiet beauty to this. If you could stand beneath a dark southern sky and know exactly where to look, you would be seeing not just a faint star, but a whole chain of interpretation. Your eye would receive light that left a star centuries ago. A telescope would gather more of it. A spectrograph would spread it out. A scientist would identify lines belonging to elements most people do not mention, outside chemistry classes or very specific crossword puzzles. Praseodymium, neodymium, holmium, strontium, yttrium. Names that sound like they belong in the back room of the periodic table, where the elements wear formal jackets and refuse to explain their hobbies. In a normal evening, these names do not feel connected to the sky, but in Przybylski's star they become astronomical clues. It is worth staying with the simple view for a moment, though, before we dive deeper into the spectrum. There is something peaceful about a faint star that does not look unusual until we listen carefully. It reminds us that reality has layers. The first layer is appearance, a point of light, a coordinate, a faint object in Centaurus. The second layer is measurement, brightness, colour, distance, motion. The third layer is interpretation. Temperature, chemistry, magnetic field, pulsation. The fourth layer is uncertainty, the part where the measurements do not settle into one easy answer. Przybylski's star occupies all of these layers at once. To a backyard observer, it is a dot. To a catalogue, it is an entry. To a spectroscopist, it is a crowded forest of lines. To a theorist, it is a problem that refuses to sit still. Centaurus as a constellation has deep old roots in the human imagination. It represents a centaur, a creature half human and half horse from Greek mythology, though like many constellations, its cultural meaning shifts depending on who is doing the naming. The modern scientific sky divides it into a defined region, a patch with borders drawn by astronomers so that every object has an official celestial address. Przybylski's star lives within that address, far south of the celestial equator. Its declination means that for many northern observers it never rises, or rises too low to be seen well. That alone gives it a slightly hidden character. Some mysteries are hidden by distance, some by faintness, some by geography. If you live too far north, this star may never climb into your sky at all. It is still there, of course, because the universe does not depend on our horizon. But your particular patch of Earth may not offer the right angle. The sky is shared, but not all at once. There is a nice reminder in that, especially for a sleepy science journey. No one sees the whole sky from one place. The Earth itself edits the universe for us. We get a portion, a rotating window, a nightly selection. To see everything, humanity has had to travel, build observatories in different hemispheres, launch telescopes above the atmosphere, and combine observations across continents. A star in Centaurus may be familiar to one observer and entirely absent to another. That makes the story of Przybylski's star feel international from the beginning. A Polish-Australian astronomer, a southern star, European and global observatories, modern space missions, atomic data from laboratories, theoretical models from researchers trying to understand how stellar atmospheres sort elements. The faint point belongs to the sky, but the effort to understand it belongs to many people. When astronomers first decide whether a star is ordinary or peculiar, colour can offer a rough clue, but colour alone is not enough. A star's colour tells us about temperature. Blue-white stars are hotter, orange and red stars are cooler. Przybylski's star is often discussed as an AP star, a chemically peculiar star related to A-type stars, though its exact temperature and apparent spectral classification have been historically difficult because its atmosphere is so strange. That difficulty is part of the charm, in the scientific sense of charm, which often means this will cause trouble for decades. If an atmosphere is full of unusual absorption lines, the usual temperature indicators can be distorted. It is like trying to judge the colour of a room through a stained glass window. The light coming through is real, but the filter complicates the picture. A faint star in Centaurus, then, becomes a test of how well we understand stars at all. It asks a very practical question. When a star's surface layers are chemically abnormal, how do we infer the deeper properties? How do we decide what the star truly is, rather than what its outer atmosphere is displaying? With most stars, the visible atmosphere gives a usable sample of the star's general condition. With chemically peculiar stars, the atmosphere can be misleading. Elements may not be mixed evenly. Some may accumulate in high layers, others may sink. Magnetic fields can hold material in place or influence how it moves. Radiation from inside the star can push certain ions upward, because those ions absorb light efficiently at particular wavelengths. Gravity pulls downward. The result can be a delicate chemical sorting process, not unlike a cosmic version of dust settling in a room while sunlight keeps lifting certain specks into the air. This is not a perfect analogy, but at bedtime we may allow dust to help explain rare Earth stars, as long as it behaves itself. The reason Przybylski's star matters is not simply that it is chemically peculiar. There are many chemically peculiar stars. Astronomers know whole classes of them, including AP and BP stars, where P means peculiar. That little letter does a lot of work. It says, in effect, please do not expect the normal pattern. Many AP stars have strong magnetic fields and unusual surface abundances of elements such as silicon, chromium, strontium, europium and others. Some pulsate, some rotate slowly. Some have abundant spots so that as the star turns, different chemical regions come into view and the spectrum changes. Przybylski's star belongs in this family, but it is the relative everyone keeps talking about after the reunion, because it brought something extremely unexpected to the table. Its rare Earth features are not merely present, they are overwhelming. The spectrum is so rich and crowded that early studies struggled to identify what was there, and later studies continued to refine the picture with better atomic data. Imagine looking at a forest from far away. At first it is just a dark green mass. Then you walk closer and see trunks, branches, leaves, shadows, vines. Now imagine trying to identify every plant in that forest by the way sunlight filters through it from miles away. That is somewhat like reading the spectrum of Przybylski's star. The lines overlap. The rare earth elements have complicated atomic structures, which means many possible transitions, many possible absorption lines. Some laboratory wavelengths are known well, others are less certain. Some features in the star can be identified confidently, others remain ambiguous. So the star is not only strange because of what it contains, or appears to contain, but because it challenges the tools used to decide what contains even means when all you have is light. For the listener lying comfortably somewhere on Earth, this may sound wonderfully remote, and it is remote, but it is also connected to a very human habit, noticing small irregularities. A detective sees a footprint that does not match. A doctor sees a symptom that does not fit the common diagnosis. A musician hears one note slightly out of tune. An astronomer sees a spectral line where the expected pattern says it should not be, or notices that the usual lines are too weak. Much of discovery begins this way. Not with a huge announcement, but with a mismatch. Przybylski's star is a mismatch with coordinates. It is the sort of object that rewards patience, because nothing about it is solved by one glance. Even its distance gives us a quiet perspective. Around 356 light-years sounds far, and it is. If you could travel at the speed of the fastest spacecraft humans have ever made, the trip would take an absurdly long time, the kind of time span that makes calendars look embarrassed. But in cosmic terms, it is close enough to be part of the Sun's broader neighbourhood. This means we can measure it fairly well compared with many distant objects. We can watch its brightness. We can study its spectrum in detail. We can compare observations across years and decades. That is important because some of its properties unfold slowly. Its possible rotation period, for example, has been suggested to be extraordinarily long, perhaps on the order of many decades or even more than a century, though that idea remains tentative and tied to magnetic measurements. A star that turns so slowly would show us almost the same face for a very long time. If ordinary stars spin like dancers, this one may rotate more like a monument deciding whether to move, but that comes later. At this stage of the journey, we are still standing at the beginning, looking towards Centaurus and allowing the star to become real in the mind. Not a myth, not an internet headline, not a vague weird star, but a physical object. It has mass, it has gravity, it has a glowing atmosphere, it radiates energy into space. It likely formed from a cloud of gas and dust like other stars, shaped by the ordinary physics of collapse, heat, pressure, and fusion. It is not outside nature. That is important. The phrase "nobody can explain" does not mean no laws apply. It means that the laws we know may combine there in a difficult, unusual, hard-to-model way. Mystery in science is not a blank wall. It is more like a locked door with many scratches around the keyhole, so picture the star as it would appear through a small telescope, a quiet point among other quiet points. Nothing in the eyepiece tells you that its atmosphere is a chemical puzzle. Nothing tells you that researchers have debated its classification, its abundances, its magnetic behaviour, and the possible presence or absence of extraordinary elements. That contrast is the heart of this part of the story. The ordinary appearance and the extraordinary evidence. The calm point and the crowded spectrum. The faint star and the enormous question. It is also a reminder that the sky has depth in more than one sense. There is the geometric depth of distance, the fact that one star may be 10 light years away, while another nearby looking point is thousands of light years behind it. There is the historical depth of light travel time, each star showing us a different age of itself. There is the physical depth inside the star, from surface atmosphere down to the hot interior where energy is made. And there is the informational depth inside the light, where each wavelength carries a trace of matter, motion and field. Przybylski's star may look flat to the eye, but its light is layered with clues. That is why astronomers return to it. Not because it is loud, but because it is dense with information. A person can spend a whole lifetime under the stars and still be surprised by how much the universe hides in small things. A faint star, a thin line in a spectrum, a tiny shift in wavelength, a brightness change measured in millimagnitudes, a pulsation lasting only minutes. None of these sound dramatic at first, yet they can open entire fields of inquiry. Przybylski's star takes several of these small signs and gathers them into one object. It is faint but nearby enough to study. It is classified but not comfortably. It is stellar, but chemically odd. It is a point of light, but also a record of atomic behaviour under conditions we cannot reproduce on that scale in any laboratory on Earth. And perhaps that is where the restful wonder of it comes in. You do not need to solve it tonight. The astronomers have not fully solved it either, and they have been very busy. For now, it is enough to know where we are looking. Southward into Centaurus, toward a faint 8th magnitude star with several catalogue names and one memorable human name, toward a light that left its source centuries ago and arrived carrying a secret written not in words, but in missing colours. Toward a star that seems modest until its spectrum is opened, at which point it becomes one of the strangest chemical displays in the known sky. There is a gentle kind of irony in the way Przybylski's star was discovered, because in one sense, it had already been seen long before anyone realised it was strange. The sky is full of objects like that. A star may be recorded, catalogued, assigned coordinates, given a magnitude, placed neatly into a list, and then sit there for decades like an unopened letter. It is known, but not understood. It has a name, but not yet a story. HD 101065 was one of those quiet catalogue stars. a faint point in Centaurus that had been noticed by survey work in the 19th century and later included in the great catalogues that organised the stellar sky. On paper, it existed. In the heavens, it shone. But no one had yet looked at its light closely enough, or perhaps suspiciously enough, to realise that this little southern star was carrying one of the strangest chemical signatures ever seen in a stellar atmosphere. That distinction matters, because astronomy often has two kinds of discovery. There is the first discovery of position, when someone records that an object is there, and then there is the deeper discovery of identity, when someone realises what kind of thing the object actually is. A comet may be seen before its orbit is known. A galaxy may be photographed before anyone understands it. Is a whole island of stars beyond the Milky Way. A pulsar may first appear as a repeated radio signal before it is understood as a spinning neutron star. Przybylski's star was not hidden in the sense of being invisible. It was hidden in plain sight, disguised as a faint and apparently ordinary entry in a catalogue. The universe had written the clue into the light, but someone had to open the light properly. The person who did that was Antoni Przybylski, a Polish-Australian astronomer working at Mount Stromlo Observatory in Australia. Mount Stromlo sits near Canberra, and before the devastating fires that would later damage the observatory in the 21st century, it was one of the important homes of southern sky astronomy. The southern sky matters greatly here. Many of the stars that are difficult or impossible to observe from Europe or much of North America become accessible from Australia. Centaurus, with all its bright stars and deep sky treasures, is one of those southern riches. So it makes a kind of geographical sense that this star's oddness would be recognised from an Australian observatory, where the southern constellations are not visitors low on the horizon, but familiar parts of the night. Przybylski himself had a life that sounds almost like it was shaped by history as much as by science. Born in Poland, trained first in Europe, eventually making his way to Australia, he became connected with Mount Stromlo and the Australian National University. He was interested in stellar atmospheres, which is important because Przybylski's star is, above all, a problem of atmosphere. Not atmosphere in the earthly sense of clouds and weather, and someone deciding whether to bring an umbrella. A stellar atmosphere is the outer visible layer of a star, the region where light finally escapes into space after being shaped by temperature, pressure, magnetic fields, and the atoms it passes through. To a star, the atmosphere is a kind of luminous skin. To an astronomer, it is the place where the star writes its chemical signature. In the early 1960s, the ordinary way to study such signatures involved photographic spectra. Today, we may imagine astronomy as digital detectors, computer pipelines, enormous databases, and screens full of precise graphs. But much of earlier 20th century spectroscopy involved glass plates, careful exposures, comparison lamps, measuring machines, and a patient human eye. Starlight would be collected through a telescope and passed through a spectrograph, spreading it into a narrow band marked with dark lines. These lines had to be inspected and identified. It was slow work, it required training, it required a tolerance for tiny marks that could mean very large things. You might say it was a bit like reading a sentence where every word had been replaced by a barcode, and the barcodes were faint, crowded, and occasionally smudged by the universe. HD 101065 had already been given a spectral classification in the Henry Draper catalogue, where it was listed as a B5 star. That classification suggested a hot blue-white star much hotter than the Sun. For many stars, such a classification gives a useful first sketch. It tells astronomers roughly what kind of object they are dealing with. But classifications are only as good as the spectra and interpretations behind them, and some stars are very good at making classification feel like trying to fold a fitted sheet in the dark. When Przybylski looked more closely, he found that HD 101065 did not behave like a normal B5 star at all. It did not even behave like an easy member of the ordinary sequence. The expected features were wrong. The familiar lines did not dominate in the way they should. The the spectrum resisted the neat label it had been given. Imagine being the person at the telescope or later at the plate seeing that mismatch. Not a dramatic explosion, not a star suddenly changing brightness. Just lines in a spectrum that should not be the strongest lines there. In a normal star of that general region of temperature, astronomers expected certain elements to appear in familiar ways. Hydrogen, helium, calcium, iron, and other common elements leave patterns that help guide classification. But in HD 101065, the usual pattern was overwhelmed by unusual marks. Lines belonging to rare earth elements appeared with startling strength. Holmium, dysprosium, samarium, neodymium, and others, often in ionized forms, were not merely present as faint little extras. They seemed to be stepping into the front row and waving politely but firmly. This is where the discovery becomes more than a simple correction of a catalogue entry. Przybylski did not merely say, "This star has been slightly mislabeled." He recognized that it was peculiar in a deeper way. Its spectrum did not fit comfortably into the standard framework of stellar classification. It had low apparent iron features compared with what one would expect, and it had enormous signs of elements that usually do not dominate stellar spectra like that. At one point, Przybylski even doubted whether iron was present in the spectrum at all, which is a striking thought. Iron is one of the most common and useful reference elements in stellar spectroscopy. It appears in countless stars and helps astronomers measure abundance, temperature, and other properties. A star whose spectrum makes iron seem absent while rare earth elements crowd the page is not just unusual. It is the sort of object that makes astronomers sit up a little straighter, even if they were hoping for a quiet evening. The beauty of the discovery is that it depended on not ignoring the discomfort. It would have been easy, in a less careful moment, to assume the spectrum was flawed, the plate was odd, the comparison was mistaken, or the star was simply too difficult to bother with. Science has plenty of tedious work, and not every oddity becomes important. Sometimes a strange mark really is an error. Sometimes a faint feature really is a defect, a blend, a calibration issue, or an instrument doing something unhelpful at the worst possible time. Instruments, like people, can have moods, though they express them in more expensive ways. But Przybylski paid attention. He took the star seriously. He allowed the strange spectrum to remain strange. That is one of the quiet, heroic acts in observational astronomy. Noticing that the data are not behaving and choosing to investigate instead of forcing them back into obedience. A catalogue can tell you where to look. A theory can tell you what you expect. But a spectrum can say, very calmly, no. And when the spectrum says no, science has to decide whether to listen. For Przybylski, the answer was to listen. The formal recognition of the star's peculiarity in 1961 is the moment the object entered astronomy's more mysterious rooms. It became not merely HD 101065, but Przybylski's star, named for the astronomer who identified its extraordinary nature. Naming a star after a person is not common in the way naming asteroids or comets can be. Most stars keep catalogue names, ancient names, Bayer letters, Flamsteed numbers, or variable star designations. So when a relatively faint star becomes known by a person's name, it usually means something about it stood out strongly enough to gather a story. This one did. It was not bright enough to be famous by eye, but it was chemically strange enough to become famous among specialists. To understand why the discovery was so startling, it helps to remember how spectral classification usually works. In the early and middle 20th century, astronomers had already built a powerful system for sorting stars by their spectra. The sequence O, B, A, F, G, K, M, with its subdivisions, was not just alphabetical decoration, even though it does look as if someone dropped the alphabet and kept the pieces that rolled under the sofa. It was a temperature sequence. Hot O and B stars show certain lines. A star shows strong hydrogen lines. Cooler F and G stars show more metal lines. K and M stars show even more complex features, including molecular bands in the coolest stars. This system turned the apparent chaos of starlight into an organized map. But chemically peculiar stars had already begun to complicate that map. Some stars, especially among the A-type group, showed unusual strengths of elements such as silicon, chromium, strontium, and europium. These were the AP stars, where the P stands for peculiar. Their peculiarity was not random. Many had strong magnetic fields and slow rotation. Many showed surface patches or vertical layers where certain elements were concentrated. But even within this family of unusual stars, HD 101065 was extreme. It was not just mildly peculiar, as if it had chosen an eccentric hat. It was peculiar in a way that made the entire outfit difficult to describe. Przybylski's first problem was classification. What kind of star was this? If the spectrum is full of rare Earth lines, and if normal temperature indicators are distorted or buried, the answer becomes surprisingly difficult. Later astronomers would debate whether it should be associated with F-type or A-type peculiar stars, whether its temperature was cooler than many AP stars, and how to interpret a spectrum whose surface chemistry was so heavily altered. That debate matters because the appearance of a star's atmosphere can mislead us about the star as a whole. If rare earth elements are concentrated in the outer layers by diffusion, magnetic fields, or radiative levitation, the visible surface may not represent the star's bulk composition. In other words, the star may be wearing a very strange coat, but that does not mean the whole star is made of coat. That may sound like a small distinction, but it is essential. When people hear that Przybylski's star contains bizarre elements, they may imagine the entire star made of exotic material, a great glowing ball of rare metals. The actual scientific picture is subtler. The mystery lives largely in the atmosphere, in the layers where light forms and escapes. Those layers can be chemically sorted. Some atoms can be pushed upward by radiation if they absorb light efficiently. Others can settle downward under gravity. Strong magnetic fields can stabilize the atmosphere and reduce mixing, allowing these separations to persist. So the visible spectrum can become deeply unusual, even if the deeper star is much more ordinary. This was not all fully clear at the moment of discovery, but it became increasingly important as astronomers tried to explain what Przybylski had found. The discovery also showed how powerful spectroscopy had become. No one needed to touch the star. No probe had to cross hundreds of light years. No spacecraft had to scoop material from its surface, which would be difficult for many reasons, including the tiny issue that the surface of a star is not a place where scoops remain cheerful. All Przybylski needed was light, collected through a telescope and dispersed into a pattern. That pattern revealed that something in the star's outer layers was deeply unusual. A faint point in Centaurus became a chemical riddle because its light, when separated carefully, refused to look normal. It is easy now, looking back, to treat the discovery as inevitable. Of course someone would find the odd spectrum. Of course the star would become famous. Of course it would be studied again and again. But scientific history rarely feels inevitable while it is happening. At the time, it was one faint star among many. The work of observing and classifying stars could be repetitive. A plate could show dozens of spectra. A researcher might spend long hours comparing lines, checking identifications, looking for patterns. Most stars would fall roughly where expected. Some would have small quirks. And then, now and again, one object would appear that made the whole routine worthwhile. HD 101065 was one of those objects. It was the unexpected sentence in a book of familiar grammar. The star's discovery also came at an interesting time in stellar astronomy. By the early 1960s, the basic idea of stellar energy through nuclear fusion was well established. The Hertzsprung-Russell diagram had become one of astronomy's great maps, showing how stars relate by luminosity and temperature. Stellar evolution was developing rapidly. Astronomers were learning how stars are born, how they age, how they leave the main sequence, and how their deaths enrich the galaxy with heavier elements. In that larger picture, chemically peculiar stars were a reminder that even when the grand structure is understood, surface details can still be wonderfully difficult. The life of a star is not only its core, it is also its atmosphere, its magnetism, its rotation, its microscopic sorting of atoms over long periods of time. Przybylski's star arrived as a vivid example of how strange those surface processes could become. After Przybylski's recognition, the star began attracting more careful study. Astronomers returned to its spectrum with better equipment, better line lists, and more advanced models. Each improvement revealed more complexity. What had first looked like a bewildering set of lines became, in later work, a sign of extraordinary rare earth overabundances. Holmium became especially notable. So did neodymium and praseodymium. The spectrum was so crowded that identifying individual lines became a challenge in itself. It was not like seeing one unfamiliar face in an otherwise empty room. It was more like entering a crowded railway station where every person is wearing a name tag in tiny handwriting, and several of the names are from the lesser-known corners of the periodic table. And because the lines were crowded, the discovery did not end in a single clean answer. That is another important point. Przybylski discovered the peculiarity, but he did not solve the entire star. Discovery is often the opening of a question, not the closing of one. The later decades would bring debates over abundance measurements, the possible presence of radioactive elements, the role of magnetic fields, the star's pulsations, and its extremely slow rotation. The first recognition was like opening a door and finding not a room, but a hallway full of more doors, each labelled in a handwriting that looked suspiciously like lanthanide spectroscopy. There is something very human about that. We often imagine discovery as a bright line between ignorance and knowledge. Before, we did not know. After, we know. But many discoveries are more like waking up to the fact that the world is stranger than yesterday's explanation allowed. Przybylski did not simply add one object to a list. He revealed that a known object had been misunderstood. He turned an ordinary catalogue point into a long-term scientific puzzle. And that kind of discovery can be more powerful than finding something entirely new, because it tells us that the familiar sky may still contain surprises if we ask better questions. The phrase, "ask better questions," is especially fitting here, because the star did not change. HD 101065 was shining before Przybylski studied it. It had the same light, the same atmosphere, the same strange spectral features. What changed was the quality of attention. A catalogue entry became a target of curiosity. A faint star became a named object. A spectrum became evidence. The universe is full of such transformations. The facts are out there, but discovery happens when attention meets them in the right way. Perhaps then the story of how Przybylski's star was discovered is also a story about humility. The star had been misclassified, or at least classified too simply, because the available information did not reveal its true character. That is not a failure so much as a natural part of science. Early catalogues were enormous achievements. They brought order to the sky. They gave future astronomers the very list from which oddities could later be found. Without the catalogues, the star might not have been so easy to locate, compare, and revisit. Science builds its mysteries on top of its earlier maps. A map that is incomplete is still valuable if it helps someone notice where the landscape does not match. And so the discovery unfolded in layers. First, a faint star was recorded in the southern sky. Then it entered catalogues under names like HD 101065. Then it received a conventional classification that seemed acceptable until more detailed observations challenged it. Then Przybylski examined its spectrum and realized that the standard framework was not enough. Then the star became a subject of deeper investigation, and the name Przybylski's star began to stand for one of the most chemically peculiar stars known. It was not one moment only, but a chain of recognition, a quiet deepening. If you imagine the scene at Mount Stromlo, do not picture a sudden dramatic shout echoing through the dome. Real discovery is often quieter. A plate under inspection, notes made carefully, lines compared. A scientist realizing that the strongest features belong to elements that should not be taking such a prominent role. The night outside perhaps cool and still, the telescope perhaps already turned to another object, the star itself far away in Centaurus, shining without concern for whether anyone on Earth is confused. There is a calmness in that image. The universe does not hurry to explain itself, it simply offers evidence and waits. That waiting is part of why the star remains compelling. From 1961 onward, astronomers had a new problem. How could a star have such a spectrum? Why were iron group elements apparently weak while rare earth elements were so strong? Was the star fundamentally unusual in composition, or was its atmosphere sorting elements in an extreme way? What role did magnetic fields play? How slowly did it rotate? Were some of the most exotic claimed lines real, or were they blends created by the crowded forest of rare earth transitions? Each question grew naturally from the discovery. Przybylski's careful attention did not end the mystery. It gave the mystery a name, and a named mystery has a way of surviving. It can be passed from paper to paper, observatory to observatory, instrument to instrument. A star named HD 101065 may sound like a database entry. A star called Przybylski's star sounds like a case file with a personality. The name invites memory. It reminds us that someone noticed. It connects the object to human effort, to the long tradition of looking at the sky and refusing to let oddness vanish into the background. That is how the star nobody can explain entered the scientific imagination. Not as a blazing object that demanded attention from every eye on Earth, but as a faint point whose light, when spread into colours, revealed a hidden arrangement of atoms. It was discovered by being read, and like many difficult texts, the first reading raised more questions than it answered. By the time astronomers realised that the faint point in Centaurus was not behaving like an ordinary star, the real work had only just begun. Finding a strange spectrum is one thing. Explaining why it looks strange is quite another. A spectrum can be generous, but it can also be stubborn. It gives you evidence, not a neat summary. Neat. It does not say, here is my temperature, here is my magnetic field, here is why my atmosphere looks like someone spilled the rare earth shelf into it. It simply spreads the starlight into lines and waits, while humans try to make sense of the pattern. And in the case of Przybylski's star, that pattern looks so unusual that one could almost imagine the periodic table itself looking over the astronomer's shoulder and whispering, "Are you sure about this?" To understand why the spectrum seemed almost impossible, it helps to begin with what astronomers normally expect. A star's light is shaped by its outer layers. Deep inside, energy is made by nuclear fusion, then works its way outward through dense plasma, scattering, shifting, and slowly escaping. By the time that energy reaches the visible surface and travels into space, it has passed through gases that leave their marks. Atoms and ions absorb particular wavelengths depending on their structure. The result is a spectrum full of absorption lines. For many stars, those lines are familiar enough that astronomers can classify the star, estimate its temperature, measure its motion, and identify its main chemical ingredients. It is one of the great quiet triumphs of astronomy that a line in starlight can tell us what kind of atom was waiting hundreds of light-year away. Most stellar spectra have a kind of order. Hot stars show certain features, cooler stars show others. Hydrogen, helium, calcium, iron, magnesium, sodium, and other common elements appear in patterns that make sense for the star's temperature and class. The lines are not simple exactly, because no real star is ever as tidy as a classroom diagram, but the overall picture is manageable. A normal spectrum is like a familiar street at night. You may not see every doorway, but you know roughly where you are. Przybylski's star is more like turning onto that street and finding that all the house numbers have been replaced by rare earth element symbols, several lamps are missing, and someone has parked a suspiciously complicated magnetic field across the road. The first great oddity is the weakness of ordinary chemical signatures compared with the strength of unusual ones. Early observers noticed that iron and nickel, elements that are usually reliable characters in stellar spectra, seem surprisingly weak. Iron is particularly important because it has many lines and is commonly used as a reference for stellar metallicity. In many stars, iron behaves like a familiar narrator. It helps you follow the story. But in Przybylski's star, iron did not narrate very loudly. Instead, the light was crowded by signatures from rare earth elements, especially lanthanides, those elements that sit in the lower rows of the periodic table and are easy to forget until a star decides to make them the main event. Praseodymium, neodymium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, ytterbium. These are not the names most people expect to meet in a bedtime astronomy story, though they do have a certain sleepy charm if you say them slowly enough. In most stars, these elements are present only in tiny amounts, and their lines may be weak or hard to notice. In Przybylski's star, many of them appear enormously enhanced in the visible atmosphere. Some studies found rare earth abundances thousands to tens of thousands of times higher than ordinary cosmic levels, depending on the element and model used. That does not necessarily mean the whole star is made of rare earth material. This is a very important point. This spectrum tells us mainly about the star's visible atmosphere, not the entire interior, but still, for the outer layers to display those elements so strongly is deeply strange. This is where the phrase chemically impossible begins to make emotional sense, even if it is not the most careful scientific wording. The star is not chemically impossible in the sense that chemistry has stopped working. Atoms have not forgotten their rules. The spectrum is not magic, but it looks chemically impossible because the surface abundances seem wildly out of balance compared with what ordinary stellar formation would suggest. Stars form from clouds of gas and dust. Those clouds carry the chemical history of earlier generations of stars, including elements forged in stellar cores, supernova, neutron star mergers, and other violent events. A star's overall composition should broadly reflect the cloud from which it formed. It should not casually present an atmosphere where rare earth elements appear in such extreme amounts while some common metals seem subdued. So the question becomes, did the star form from a bizarrely enriched cloud, or did something happen later in its atmosphere? The more plausible answer is that the star's atmosphere has been altered by internal sorting processes. Przybylski's star belongs to the family of chemically peculiar magnetic stars. In such stars, the outer layers can be stable enough that elements separate rather than mix evenly. Gravity pulls atoms downward. Radiation from below pushes certain ions upward, especially if they absorb light efficiently. A magnetic field can reduce turbulence and organize the movement of charged particles. Over long spans of time, this can create chemical stratification, meaning different elements gather at different heights, and sometimes in different surface regions. It is a little like a jar of mixed grains left undisturbed while invisible hands gently lift some grains and let others settle. After a while, the jar no longer looks mixed at all. For many AP stars, this idea explains a great deal. Their strange spectra come from atmospheres that are not well stirred. Some elements rise, others sink, and magnetic fields preserve the pattern. But Przybylski's star takes this explanation to an extreme. If the usual chemically peculiar star is a cupboard where a few jars have been placed on the wrong shelf, this one is a cupboard where the entire lower half of the periodic table appears to have reorganized itself by moonlight. The rare earth lines are so strong and numerous that they crowd the spectrum. They blanket it. They interfere with the normal temperature indicators. They make it hard to tell which lines belong to which atoms. They even make it hard to build a model atmosphere that behaves sensibly, because the light opacity, the way material absorbs radiation, is changed by the huge number of metal lines. That is part of what made classification difficult. A star's spectrum is often used to estimate its temperature, but what if the spectrum is so chemically distorted that the usual signs are buried or altered? A normal F-type or A-type star might show patterns that let astronomers identify it fairly confidently. But in Przybylski's star, the surface chemistry is so peculiar that the spectrum itself becomes a mask. Hydrogen lines, metal lines, rare earth lines, ionized species, blended features, all of them combine into a signal that does not easily match the standard categories. The star may be only somewhat hotter than the Sun, but its spectrum is unlike a normal star of that temperature. It is not just a thermometer, it is a thermometer covered in rare earth stickers. The problem becomes even harder because rare earth elements have complicated atomic structures. Many electrons, many energy levels, many possible transitions. Each transition can make a line. In a high-resolution spectrum, these lines pile up by the thousands. Some are known from laboratory measurements, some are less certain, some overlap with lines from other elements. This overlapping is called blending, and in Przybylski's star, blending is not a minor inconvenience. It is one of the main characters. When a spectral feature appears at a certain wavelength, astronomers must ask whether it belongs to one element, another element, a combination of several, or something not yet properly measured in laboratory data. A clean line is a straightforward clue. A blended line is more like hearing three people answer at once and trying to decide who said what. This is especially important when we come to the more dramatic claims. Przybylski's star has been associated over the years with possible signs of radioactive elements, including promethium and technetium, and even heavier actinides in some studies. This is where the story often becomes exaggerated in popular retellings. Promethium has no stable isotopes. Technetium is also radioactive. If such elements were truly present in the atmosphere in detectable amounts, astronomers would need to explain how they are being produced, supplied, or preserved, because they should not simply survive for long cosmic timescales in ordinary conditions. That is an astonishing thought. It is also exactly the kind of thought that must be handled carefully, with both curiosity and restraint. The reason for caution is simple. The spectrum is crowded. Almost everything is blended. A possible promethium line may lie near lines from other neutron capture elements. A possible technetium feature may be part of a complex absorption blend that can be explained without requiring technetium to be clearly present. Recent analyses have revisited some of these claims and concluded that, at least for certain lines, the evidence is not strong enough to say definitively that those radioactive elements are there. That does not make the star ordinary. It makes the science better. A mystery does not become weaker when we remove shaky evidence. It becomes cleaner. The real strange features remain, and they are already strange enough without needing to decorate them with every possible exotic claim. Still, the fact that astronomers even have to ask these questions tells us how unusual the spectrum is. In most stars, no one is seriously checking whether promethium lines might be hiding in the atmosphere. That is not a normal Tuesday in stellar classification. With Przybylski's star, the spectrum is so rare earth rich, so crowded and so chemically extreme that even unusual identifications become tempting enough to investigate. It is like searching through a wildly overstuffed attic and wondering whether one of the boxes contains something that should not exist there at all. You may eventually decide it is just an oddly shaped lamp under a blanket, but the search itself tells you the attic is not ordinary. Another feature that complicates the spectrum is ionization. Atoms in a star's atmosphere are often missing one or more electrons because of the high temperature and radiation. A neutral atom and an ionized atom of the same element produce different lines. Neodymium, for example, may appear as Nd2 or Nd3, meaning it has lost one or two electrons. In some rapidly oscillating AP stars, rare earth elements show strong lines from doubly ionized species, and these can form at different heights in the atmosphere. This matters because the star is not chemically uniform from bottom to top. Different lines may come from different layers. One element might be concentrated high above the layers where another element forms its lines. So the spectrum is not a simple flat chemical list. It is a vertical map, but one we see only through light, and the map has been folded several times before it reaches us. Think of the atmosphere as having layers, not like hard shells, but like regions where pressure, temperature, and composition change gradually. In a normal, well-mixed atmosphere, those layers may still be complex, but the chemical composition does not vary wildly. In a star like Przybylski's star, the atmosphere may be strongly stratified. Rare earth ions could gather high in the atmosphere, while other elements sit lower down. A magnetic field may influence how this happens. Pulsations may move material or change line shapes. The result is that a line from one ion of an element may suggest a very different abundance than a line from another ion of the same element. That is not because the atom is lying. It is because the lines are forming in different physical environments. The star is not a single chemical photograph. It is more like a stack of transparent pages, each with different markings, all viewed at once. This is why astronomers need model atmospheres. They do not simply look at a line and say, "Ah yes, 10,000 times normal, off to lunch." They calculate how light should pass through an atmosphere with a given temperature, pressure, gravity, composition, and magnetic field. They compare synthetic spectra with observed spectra. They adjust parameters, they check laboratory wavelengths, they ask whether the line strength can be reproduced. For Przybylski's star, this is difficult because the very elements being measured also affect the structure of the atmosphere. Heavy line blanketing changes how radiation moves. The abundance pattern changes the pressure and temperature structure. The spectrum is both evidence and interference, both clue and complication. It is a bit like trying to weigh a cat while the cat is rearranging the scale. And then there is the magnetic field. Magnetic fields can split spectral lines through the Zeeman effect, where a line divides into components depending on the strength and orientation of the field. In some stars, this splitting can be measured directly. Magnetic fields can also help stabilize the atmosphere and guide diffusion, allowing peculiar abundance patterns to persist. Przybylski's star is magnetic, and that magnetism is not a decorative detail. It is probably central to why the star's outer layers are so chemically peculiar. Without a stable, magnetically influenced atmosphere, turbulence and convection would mix material more thoroughly, softening the extreme separations. But in this star, the outer layers may be calm enough, at least in the relevant sense, for atoms to sort themselves over long periods. The idea of a calm atmosphere producing a wild spectrum is pleasingly strange. We often associate dramatic results with violence, explosions, collisions, eruptions, things going bang in the night. But Przybylski's star may owe much of its weirdness to stillness, slow rotation, strong magnetism, reduced mixing, a quiet atmosphere where small forces can work patiently. Radiation nudges, gravity tugs, magnetic fields hold the arrangement steady. Given enough time, these subtle effects create a surface chemistry that looks outrageous. The star is not necessarily exploding exotic material into existence. It may be sorting ordinary traces into extraordinary visibility. That is a different kind of wonder, less fireworks, more cosmic bookkeeping gone beautifully strange. But sorting alone may not answer every question. The extreme rare earth enhancements remain hard to model in detail. Some elements appear far more abundant than expected even for peculiar stars. The lanthanide to iron ratio is especially striking. The atmosphere seems to favour rare earth signatures so strongly that it stands apart even among AP stars. That is why the spectrum has kept its reputation. Many stellar oddities become less odd once better data arrive. Przybylski's star has become better understood in some ways, but not boring. Better data did not flatten the mystery, they sharpened it. It is also important to remember that abundance values depend on assumptions. When astronomers say an element is overabundant by a certain number of decs, they're using a logarithmic scale and a model. A difference of 1 dex means a factor of 10. 5 decs means a factor of 100,000. These numbers can sound almost comically large, as if the star is exaggerating for attention. But they refer to the visible atmosphere under the model being used. Change the model, account for stratification, include better atomic data, and the exact numbers may shift. The overall picture remains. Rare earth elements are extraordinarily enhanced in the spectrum, but the precise values are part of an ongoing scientific effort, not stone tablets carried down from Mount Spectrograph. This carefulness matters because Przybylski's star sits near the boundary between genuine mystery and tempting mythology. It is strange enough to invite wild ideas. Some have speculated about exotic nuclear processes, unknown super-heavy elements decaying into observed products, or other unusual mechanisms. These ideas are not all equal and many remain speculative. The safer, stronger foundation is the observed spectrum, extreme rare earth enrichment, weak or unusual iron peak signatures, magnetic peculiarity, atmospheric stratification, rapid oscillations and uncertain claims about some radioactive species. That foundation is already fascinating. We do not need to pretend the star violates physics. It challenges our ability to apply physics cleanly to a complicated atmosphere. In a way, the phrase, almost impossible, is best understood as a human reaction. The spectrum looked almost impossible because it didn't match the expectations built from more ordinary stars. It looked like a mistake until the observations proved it was not simply a mistake. It looked like a chemistry problem until it became a physics problem. It looked like an abundance problem until it became an atmospheric structure problem. Each step moved the mystery from one drawer to another, but none of the drawers closed all the way. Imagine, for a quiet moment, the light leaving the star. It rises through layers where rare earth ions absorb very specific wavelengths. It passes through a magnetic environment that may split and shape lines. It carries the imprint of slow rotation, pulsation, temperature, gravity, and chemical stratification. Then it crosses hundreds of light years of space, enters Earth's atmosphere, passes into a telescope, and is spread into a spectrum on a detector. What arrives is not a picture of the star, but a coded record of its outer layers. And when astronomers decode that record, the message is not nonsense. It is not random. It is precise, but difficult. It says, in effect, this atmosphere has been altered in a way you do not yet fully understand. That is why the spectrum of Przybylski's star remains so compelling. It is one of the rare cases where the fine print of starlight is more dramatic than the star's appearance. To the eye, a faint point. To the spectrograph, a chemical storm. To a modeler, a headache with coordinates. To the rest of us, listening quietly, it is a reminder that the universe can hide its strangest rooms behind ordinary doors. Once we accept that the spectrum is real, and not just a mistake, we have to ask what those rare earth elements are doing there in such strength. How can a star's atmosphere become so enriched with materials that should only appear as traces? Why do these heavy atoms rise into visibility, while more familiar ones fade into the background? Once the spectrum of Przybylski's star was opened and studied with more care, the mystery became less like a single locked door, and more like a whole hallway of them. The first strange impression was not just that the star contained unusual elements. Many stars contain unusual traces of material, if you examine them closely enough. The deeper shock was the balance. The ordinary ingredients seemed too quiet. The rare ingredients seemed too loud. Iron, one of the most useful and common signposts in stellar spectroscopy, appeared weak. The rare earth elements, which usually keep to the background like guests who do not wish to trouble the host, had moved forward and taken over large parts of the conversation. It was not simply a star with a few odd lines. It was a star whose fingerprints in light seemed to belong to a chemical personality almost no one expected. Let's stay with that idea of fingerprints for a moment, because it is one of the easiest ways to understand why astronomers were so startled. Every element has a structure inside its atoms. Electrons sit in particular energy levels, and when light passes through gas made of those atoms, certain wavelengths are absorbed. The atom is not choosing colours in the way a person chooses socks, although frankly, the periodic table has made some bold wardrobe decisions. It is responding to the laws of quantum mechanics. Only certain amounts of energy can move an electron from one level to another, so only certain wavelengths are absorbed or emitted. Those wavelengths become lines in a spectrum. Hydrogen has its own pattern, iron has its own pattern, calcium, sodium, magnesium, titanium, and all the rest have their own patterns too. When many elements are present in a star's atmosphere, the spectrum becomes a layered record of all those atomic signatures. In an ordinary star, the familiar elements guide the interpretation. Hydrogen lines help with temperature, iron lines help with abundance, calcium and magnesium lend their own clues. The iron peak elements, those around iron in the periodic table, are especially important because they are common enough and line-rich enough to be useful. They appear in many stars, they are well studied, and they often form the backbone of abundance analysis. Iron is not always exciting, but it is dependable, and in science dependability is underrated. It is the element that shows up with a clipboard and says, let's measure this properly. So when the early studies of Przybylski's star found iron and nickel looking unusually weak, that was already a serious puzzle. The reliable characters had gone quiet. At the same time, the rare earth elements had become strangely prominent. These are mostly the lanthanides, elements from lanthanum through lutetium, plus related elements that often behave in chemically similar ways. On Earth, we use some of them in magnets, electronics, lasers, screens, and specialized materials. In the sky, they're important because many are made through neutron capture processes in extreme astrophysical environments. But in normal stellar atmospheres, they do not usually dominate the visible spectrum. They are usually present in small amounts, and their signatures can be subtle. In Przybylski's star, however, rare earth lines appear with remarkable strength. Praseodymium and neodymium are especially famous in the story. Holmium also became one of the star's signature clues. Some classifications even emphasize strong holmium features, which is not the sort of thing most stars can put on a resume. The names themselves sound almost unreal when placed inside a bedtime science narration. Praseodymium, neodymium, dysprosium, holmium, europium, gadolinium, terbium, erbium, ytterbium. They seem less like the contents of a star and more like a list of small kingdoms in a fantasy map, but they are real elements, and their spectral fingerprints are real. The problem is not that these atoms cannot exist in a star. The problem is that in this star's visible atmosphere they appear far too strongly compared with what astronomers would normally expect. Some studies describe rare earth abundances as enhanced by enormous factors compared with standard cosmic values. That means the outer layers are not behaving like a well-mixed sample of the material from which the star originally formed. Something has changed the way elements are distributed near the surface. This is why the weak iron matters so much. A star rich in rare earth signatures is unusual. A star rich in rare earth signatures while iron appears relatively weak is stranger still. Iron is made in great quantities across cosmic history. It is one of the major products of stellar evolution and supernova activity. The Milky Way is full of stars whose compositions are often described in relation to iron because it is such a useful reference. If a star simply formed from a cloud that was unusually rich in heavy elements, one might expect iron and other common metals to be enhanced as well. But Przybylski's star does not present that simple picture. It looks chemically selective. Some elements are displayed with enormous strength, while others seem subdued. That selectiveness points away from the idea that the whole star was born from an impossibly strange cloud, and toward the idea that its outer atmosphere has been sorting elements. and sorting in a star is a quiet but powerful thing. We tend to think of stars as boiling, turbulent, violently mixed objects, and many are. The sun's outer layers churn with convection. Hot plasma rises, cools, sinks, and rises again. It is not a calm place, whatever peaceful face it gives us from 93 million miles away. But some stars, especially certain chemically peculiar A-type stars, can have much more stable outer atmospheres. If the atmosphere is not being thoroughly stirred, tiny forces can act over long periods. Gravity pulls atoms downward. Radiation pushes some atoms upward. Magnetic fields guide charged particles and suppress certain kinds of mixing. Given enough time, these small effects can create very large surface differences. This process is often called atomic diffusion. It sounds technical, but the idea is not too difficult. Different atoms interact with light in different ways. If an ion absorbs radiation strongly at certain wavelengths, the outgoing starlight can push on it. This is called radiative levitation. It can lift certain elements upward in the atmosphere, or keep them suspended higher than they would otherwise be. Meanwhile, gravity tries to make heavier particles settle downward. The balance between those forces depends on the element, the ionization state, the local temperature, the magnetic field, and the structure of the atmosphere. It is not one simple elevator carrying all atoms to the same floor. It is more like a very picky hotel lift that only responds to certain guests, ignores others, and occasionally takes neodymium to the penthouse. In Przybylski's star, this sorting may have operated in an unusually extreme way. Rare earth ions may have been lifted or concentrated in layers where their spectral lines become very visible. Iron peak elements may have settled differently, or may not be concentrated in the same layers where the strongest lines form. The result is a visible atmosphere that no longer reflects a normal cosmic mixture. It is not that the star's core is necessarily made from rare earth material, or that the whole star lacks iron. The spectrum is showing us the outer layers, and those outer layers may be chemically stratified. That word, stratified, simply means arranged in layers. In Earth's atmosphere, temperature and pressure change with height. In a peculiar star's atmosphere, chemical abundance can also change with height. One element may be abundant in a higher layer, another lower down. Light emerging from the star passes through all of this, and the final spectrum is the combined result. That is why Przybylski's star can be so difficult to interpret. A normal abundance analysis often assumes a relatively simple atmosphere. You measure line strengths, compare them to models, and estimate how much of each element is present. But if elements are concentrated at different heights, if the magnetic field affects the line shapes, if pulsations move the atmospheric layers, and if rare earth lines are crowding nearly every useful wavelength region, then the analysis becomes much more complicated. It is not like reading a clear label on a jar. It is like reading labels through several layers of glass, while the jars are sorted by a rule nobody has written down. The rare earth elements themselves add another level of trouble, because their spectra are complicated. Atoms with many electrons have many possible energy transitions. Many transitions mean many lines. Some lines are strong, some are weak, some are known precisely from laboratory work, some are less certain. For elements like neodymium and praseodymium, astronomers may see lines from singly ionized atoms and doubly ionized atoms, such as Nd2 and Nd3, or Pr2 and Pr3. These different ions can form at different heights in the star's atmosphere. In many rapidly oscillating AP stars, the rare earth elements seem to be concentrated high above the layers where more ordinary metal lines form. That means the spectrum is not just telling us what is present, it is hinting at where in the atmosphere each signal comes from. There is something almost restful about the patience of this process, even though the result is so strange. No explosion is needed, no collision is required, no alien engineer has to be stationed nearby with a box of lanthanides and an unusually specific plan. Over long spans of time, starlight itself may help sort the atoms. The star's magnetic field may keep the atmosphere quiet enough for the sorting to persist. Rotation may be slow enough that the chemical patches and layers are not rapidly smeared out. Each day, each year, each century, radiation pushes, gravity pulls, the magnetic field steadies, and the visible surface becomes more peculiar. The star's strangeness may be the result of very small effects given a very long time to work, which is, in its own way, one of the universe's favourite tricks. But even with diffusion and magnetic fields, Przybylski's star remains extreme. The rare Earth abundance pattern is so unusual that it stands apart from other AP stars. Many chemically peculiar stars show strong lines of strontium, chromium, europium, or silicon. Many have magnetic fields. Many rotate slowly, but HD 101065 is famous because its lanthanide signatures are overwhelming and its iron peak features are unusually weak in comparison. That ratio matters. It is not only what is there, but what is there relative to everything else. A pinch of a rare ingredient in a soup is interesting. A soup in which the rare ingredient seems to have replaced the main broth is a different kind of event, and probably one that should be discussed before dinner. This is where the phrase missing iron needs a little care. Early impressions suggested that iron was almost absent, and Przybylski himself doubted whether iron could be seen in the spectrum. Later work found that iron peak elements are present, though their signatures are weak compared with the rare Earth forest. So iron is not truly missing in the sense that the star has no iron at all. It is missing from the starring role. It has been pushed into the background of the visible evidence. That distinction is important because the popular version of the story can become too dramatic. A star with no iron and impossible radioactive elements sounds thrilling, but the real science is more subtle. Iron exists, but it is not behaving in the expected way. Rare Earth elements are present with extraordinary strength. The atmosphere is structured in a way that makes ordinary assumptions unreliable. That is enough mystery. We do not need to make it louder than it is, and yet the real version may actually be more interesting than the exaggerated one. If the whole star were simply made of impossible material, we could label it impossible and move on, though with some concern. But a star whose atmosphere has physically sorted itself into a strange chemical display gives us something to learn. It shows how microscopic atomic processes can reshape the visible face of a star. It reveals the importance of magnetic fields in stellar atmospheres. It asks how radiation, gravity, and slow rotation can work together. It turns a faint point of light into a natural laboratory for physics that is difficult to reproduce on Earth. A sensational mystery may be exciting for a moment. A real scientific mystery can stay interesting for decades. The fingerprints in Przybylski's light are also strange because they can hide one another. A spectrum full of rare Earth lines is not a clean row of neat marks. It is crowded, blended, layered. If one line appears at a certain wavelength, astronomers must check whether it belongs to neodymium, praseodymium, holmium, iron, another rare Earth element, or several of them at once. Blending is one of the great practical headaches here. A spectral line may not be a single line at all, but several lines overlapping. With an ordinary star, blending can already be a nuisance. With Przybylski's star, it becomes a whole weather system. There are so many unusual lines that identifying one feature can require careful comparison with atomic databases, synthetic spectra, and laboratory wavelengths. This is why the work of laboratory physics matters to astronomy. A telescope gathers the starlight, but a laboratory helps decode it. Scientists measure atomic transitions on Earth, identify wavelengths, calculate oscillator strengths, and build line lists. Without accurate atomic data, the star's spectrum would be much harder to interpret. The light arrives with the marks of atoms, but the key to the marks is built through experiments and calculations. So when astronomers study Przybylski's star, they are not only doing observational astronomy, They are relying on atomic physics, spectroscopy, magnetic field theory, stellar atmosphere modelling, and careful statistical methods. The faint point in Centaurus becomes a meeting place for many sciences. There is a lovely humility in that. We sometimes talk about a star as if it were one object and one problem, but to understand even a single star properly, we need a chain of knowledge. We need telescopes built by engineers. We need detectors cooled and calibrated. We need models of light moving through gas. We need quantum mechanics to explain atomic lines. We need laboratory measurements of rare elements. We need stellar physics to understand temperature and gravity. We need magnetic theory to understand line splitting and atmospheric stability. A single absorption feature in the spectrum of HD 101065 is not just a mark, it is the endpoint of a huge human effort to read nature accurately. And still, the star resists. That is perhaps why it has kept its charm. Better instruments did not simply make the puzzle vanish, they revealed that the puzzle had finer detail. The rare earth lines became clearer, the difficulty of identifying blends became more obvious. The weakness of iron peak signatures remained important. The stratification of praseodymium and neodymium became part of the story. The magnetic and pulsational behaviour added more layers. Every time astronomers sharpened the view, the star seemed to say, "Good, now notice this as well." For you, listening quietly, there is no need to keep every element name in memory. You do not have to remember whether terbium is before dysprosium, or whether ytterbium sounds like something a wizard would keep in a cupboard. The main idea is gentler than the chemical list. Przybylski's star looks chemically strange because the light from its atmosphere is dominated by elements that should usually be faint, while some of the elements astronomers expect to rely on appear unusually weak. Its surface is not a simple sample of the star's birth material. It is a sorted, magnetically influenced, slowly changing display where rare atoms have been made visible far beyond expectation. This is also why its spectrum feels like a fingerprint unlike any other. Human fingerprints are made of ridges and loops, each one a pattern. Stellar fingerprints are made of absorption lines, each one tied to atomic physics. Most stars have fingerprints that place them comfortably among relatives. Przybylski's fingerprint says, "I belong to the chemically peculiar magnetic family, yes, but please do not assume I am ordinary even there." It is a member of a known group, and an outlier inside that group. It is not unknowable, but it is not easily explained. That tension is what makes it so compelling. There is another quiet point to make here. The rare earth elements in the spectrum are not rare because they are mysterious in a supernatural sense. They are rare because the universe does not make them in the same huge amounts as hydrogen, helium, oxygen, carbon, or iron. Many are built through neutron capture processes, where atomic nuclei absorb neutrons and then decay into heavier elements. Some of these processes happen in aging stars, others happen in explosive or extreme environments. The material eventually spreads into interstellar space and becomes part of later generations of stars and planets. So when we see rare earth elements in a star's atmosphere, we are seeing traces of earlier cosmic history, rearranged by the star's own surface physics. The atoms may have been born in ancient violence, but in Przybylski's star they are displayed by quiet atmospheric sorting. That contrast is almost funny in the most cosmic way. Somewhere in the deep past, massive stars exploded or neutron-rich processes built heavy atoms. Those atoms drifted through space, became part of a cloud, entered a star, and then, much later, were lifted or concentrated in its atmosphere by delicate forces. The result is a faint point in Centaurus, whose light now puzzles astronomers on Earth. The story moves from violent creation to careful measurement, from neutron capture to spectral line lists, from deep time to a human eye noticing that iron looked too weak. As the spectrum is studied more closely, the rare earth forest leads naturally toward an even stranger question. If the atmosphere can show such extreme heavy element signatures, could it also show elements that should not last? Could some of the lines belong to radioactive elements with short half-lives, elements that decay away too quickly to sit around casually in a star for millions or billions of years? By now, Przybylski's star has already earned its reputation without needing anything extra. A faint point in Centaurus, a spectrum crowded with rare Earth elements, weak iron peak signatures, an atmosphere that seems sorted in ways ordinary stars do not display, and a place among the most chemically peculiar stars ever studied. That would be enough for one quiet cosmic mystery. Most stars would stop there, take the compliment, and let astronomers spend the next few decades politely untangling the details. But HD 101065 has never been especially interested in making things simple. Once researchers began looking deeper into its heavy element forest, a more unsettling possibility appeared. Some of the spectral lines seemed as if they might belong to radioactive elements, elements that should not last long enough to sit calmly in the atmosphere of an old star. This is where the story becomes delicate, because it is very easy to rush ahead and say something dramatic. It is tempting to say that Przybylski's star contains impossible elements, or that its surface is being constantly refreshed by a hidden nuclear process, or that it is a cosmic factory making unstable atoms in plain sight. You can almost hear the headline clearing its throat. But the real science is more careful, and in many ways more interesting. The mystery is not simply that radioactive elements have definitely been found there. The mystery is that the star spectrum is so strange, so crowded, and so rich in heavy elements that astronomers have seriously investigated whether some of its lines might come from elements that decay away far too quickly to be casually present. Some claims have been made. Some have been questioned, some have been weakened by newer work, and the star remains strange even after the more dramatic possibilities are treated with caution. Let's start with radioactivity itself, gently, without turning the pillow into a physics exam. An element is radioactive when its atomic nucleus is unstable. Over time, it changes into another nucleus by releasing particles or energy. This change is called radioactive decay. Some radioactive isotopes decay very quickly in fractions of a second. Others last for years, thousands of years, millions of years, or even billions of years. The time it takes for half of a sample to decay is called the half-life. It is not a timer that says exactly when each individual atom will change. It is a statistical measure, a way of describing how a large group behaves. If you had a jar of radioactive atoms, which I do not recommend keeping next to the biscuits, the half-life tells you how long it takes for half of them to transform into something else. In astronomy, radioactive elements can be useful clues. They can reveal recent nucleosynthesis, meaning the creation of new atomic nuclei. Technetium, for example, has played an important role in studying certain giant stars. Because technetium has no stable isotopes, finding it in the atmosphere of an aging red giant can show that the star has recently produced it inside and dredged it up to the surface. In that context, technetium makes sense. The star has internal nuclear processes, mixing episodes, and a way to bring freshly made material upward. The element is not expected to survive forever. It is evidence of something happening on a relatively recent timescale. It is like finding warm bread on a table and reasonably concluding that someone has been baking, rather than assuming the bread has been warm since the Stone Age. But Przybylski's star is not a cool red giant with deep convective dredge-up. It is a chemically peculiar magnetic star, a very different kind of object. Its outer layers are strange, yes, but not in the same way as the atmosphere of a star actively bringing newly made material from deep nuclear regions to the surface. So if short-lived radioactive elements were truly present in its atmosphere, astronomers would need an explanation. How are they getting there? Are they being produced near the surface? Are they being replenished from outside? Are they the decay products of heavier unstable nuclei? Are the spectral lines being misidentified? Or is the star's crowded spectrum playing one of those tricks that makes astronomers look thoughtfully at the data and then cancel their evening plans? Promethium is one of the most famous names in this part of the story. It sits between neodymium and samarium in the periodic table and has no stable isotopes. That alone makes it unusual. On Earth, promethium is not found in lasting natural deposits because it decays away. It can be produced in nuclear reactors or by certain decay chains, but it is not an element that simply accumulates and stays put over geological timescales. Its longest-lived isotope lasts only on the scale of years, not millions or billions of years. So the possible presence of promethium in the spectrum of Przybylski's star raised an obvious question. If it is there, what is making it, or what is supplying it? Older studies explored that possibility by searching for promethium lines in the star's spectrum. In principle, this is exactly how one would look for any element. Find the laboratory wavelengths where promethium should absorb light, then check whether the star's spectrum has matching features. But in practice, Przybylski's star is not a clean laboratory lamp. Its spectrum is full of rare earth lines: neodymium, praseodymium, samarium, dysprosium, gadolinium, and their neighbours fill the spectrum with so many marks that a possible promethium line rarely stands alone. It may sit inside a blend, meaning other elements are absorbing light at nearly the same wavelength. A feature that looks promising at first can turn out to be mostly something else. This is not failure. This is spectroscopy being honest about how difficult the star is. A more recent attempt to examine promethium in HD 101065 came to a cautious conclusion. The researchers selected and analysed candidate promethium lines, but found that almost all were heavily blended with lines from other neutron capture elements and other species. Their conclusion was not that promethium was absolutely impossible, but that the evidence was not strong enough to claim its presence definitively. That is a very important difference. Science often lives in those careful phrases: not confirmed, not ruled out in every imaginable way, not strong enough, too blended, upper limit. These words may seem less exciting than a grand declaration, but they are how knowledge stays trustworthy. They keep the story from becoming louder than the evidence. Technetium has a similar role in the mystery. Like promethium, technetium has no stable isotopes. Its longest-lived isotopes last much longer than promethium's, but still not long compared with the lifetime of a star. In some types of stars, technetium can be a sign of recent internal nucleosynthesis. But again, Przybylski's star is not the usual place where astronomers expect such a sign. A modern re-examination of technetium in its spectrum focused on candidate lines, and found that the possible features were heavily blended. One important resonance line, once considered a candidate, was judged not clearly visible in the spectrum. The newer work reduced the technetium abundance to an upper limit rather than a confident detection. In plain language, that means the data do not require technetium to be there. This does not make the story less strange. It makes it more scientifically interesting. There is a big difference between a mystery made of certainty and a mystery made of ambiguity. Przybylski's star gives us ambiguity in a very concentrated form. Its spectrum contains so many heavy element lines that researchers have to ask whether some unusual features belong to radioactive elements. But the very crowding that makes the question tempting also makes the answer difficult. The star is like a room full of people speaking rare languages all at once. You may hear a word that sounds familiar, but before you can be sure, 3 other voices overlap it. The problem is not lack of information. It is too much information packed into too little wavelength space. Then there are the actinides, the heavy radioactive elements beyond actinium, including names like thorium, uranium, plutonium, americium, curium, and others. Some studies and conference reports have explored possible actinide signatures in the spectrum of Przybylski's star. Thorium and uranium are especially interesting because some isotopes can last long enough to be astrophysically meaningful. Other actinides are much shorter lived. If several short-lived actinides were truly present, that would be even harder to explain. Ideas have been proposed, including the possibility that long-lived heavy nuclei decay into shorter-lived species, or that some process near the stellar surface produces or replenishes unstable elements. But these ideas remain challenging, and the identifications are difficult because the atomic data and blends are complicated. Here again, caution is not the enemy of wonder. It is the thing that lets wonder survive contact with evidence. If a spectral feature is assigned to an actinide, astronomers must ask how certain the wavelength is, whether a more common element could produce the same absorption, whether the line strength fits, whether the model atmosphere is reliable, whether magnetic splitting changes the profile, and whether the abundance implied by one line agrees with other lines. A single tempting match is not enough, especially in a spectrum like this. Przybylski's star is a place where line identification itself becomes a scientific challenge. It is not just asking what element is there, it is asking, how do we know what any one line means when thousands of rare Earth transitions are tangled together? Now, suppose for a moment that some short-lived radioactive element really were present. What could explain it? One idea is irradiation by neutrons. Neutrons can be captured by atomic nuclei, building heavier isotopes and sometimes creating radioactive elements. If the surface layers of the star were somehow being bombarded by free neutrons, that could, in principle, produce unstable nuclei. But free neutrons do not last long on their own, and creating a steady neutron source near the surface of a star like this is not straightforward. Another idea involves energetic particles guided by magnetic fields. In a magnetic star, charged particles can be accelerated and directed, perhaps creating unusual nuclear reactions in the atmosphere. But again, turning that broad idea into a detailed model that produces the right elements in the right amounts is difficult. A more exotic possibility sometimes mentioned is a compact companion, perhaps something like a neutron star supplying particles or influencing the atmosphere. That sounds dramatic because it is dramatic. A neutron star companion would be an extraordinary hidden partner, a dense remnant of a dead, massive star, potentially capable of producing high-energy particles or unusual irradiation. But the evidence for such a companion in Przybylski's star is not established in the way one would need for a confident explanation. There has also been discussion of a faint nearby source, but modern astrometric data suggest that at least one candidate nearby star may simply be an optical alignment rather than a true companion. So while companion-based ideas can be explored, they cannot be treated as the answer. Another idea is accretion. Perhaps the star's atmosphere has been contaminated by material from outside, such as interstellar matter, debris from a companion, or processed material from some past event. Stars can accrete material, and chemically peculiar stars may display surface contamination in certain circumstances. But again, the pattern in Przybylski's star is not easy to reproduce. It is not enough to sprinkle heavy elements onto the surface. The abundance pattern, the stratification, the magnetic atmosphere, the rare earth dominance, and the weak iron peak features all have to fit together. A good explanation must be more than a label. It must match the data. The simplest broad framework remains the same one we have already met: a stable magnetic atmosphere where atomic diffusion produces extreme chemical separation. That can explain much of the rare earth strangeness without requiring ongoing production of short-lived radioactive elements. It also helps explain why some elements are enhanced while others are depleted, but whether diffusion alone can account for every reported line and every heavy element pattern is still a difficult question. Przybylski's star may be a case where a known process operates in an extreme regime, or it may require additional effects, perhaps weak stellar winds, stratification, magnetic geometry, or some kind of external influence. The star does not hand us one clean lever and say, "Pull here for explanation." There is also a psychological lesson in this radioactive part of the story. Humans are drawn to the most dramatic possibility. If a star might contain promethium, that fact catches the imagination more quickly than a careful discussion of line blending. a star with radioactive elements that should not exist, travels faster than a chemically peculiar ROAP star with highly uncertain identifications of unstable species in a crowded rare earth spectrum. The second sentence is more accurate, but it does not fit as neatly on a thumbnail. And yet, for this quiet journey, the second sentence is the one worth staying with. It respects the star. It respects the astronomers. It respects the uncertainty. Because uncertainty here is not emptiness. It is structured. We know that Przybylski's star has an extraordinary rare earth spectrum. We know that iron and nickel are weak compared with ordinary expectations. We know that the atmosphere is chemically peculiar, magnetic, and likely stratified. We know that some proposed radioactive element identifications are difficult because of heavy blending. We know that newer work has not confirmed promethium and has cast doubt on technetium. We know that the question remains scientifically interesting because the spectrum is unusual enough to keep these searches meaningful. That is not a lack of knowledge. That is a map with several foggy regions, and foggy regions are still part of the map. The half-life issue is what gives this mystery its sharp edge. If an isotope lasts only years, decades, or even thousands of years, it cannot simply have been sitting unchanged in a stellar atmosphere since the star formed. Stars like this are not young in that sense. Their lifetimes are long. Any truly short-lived isotope must be newly made, newly supplied, or misidentified. Those are the options. Newly made means some nuclear process is happening near the surface or in a way that can deliver products to the surface. Newly supplied means material is arriving from outside. Misidentified means the spectral feature belongs to something else. Most of the time, the conservative answer is the last one until evidence says otherwise. But Przybylski's star keeps the other possibilities hovering at the edge of the discussion because its whole spectrum is already unusual. There is a soft kind of drama in that scientific restraint. No one needs to shout. The situation itself is enough. A faint star in Centaurus shows thousands of lines. Many belong to rare earth elements. Some features sit near wavelengths where radioactive elements might absorb. Researchers compare, synthesize, question, reject, revise, and try again. Promethium becomes a maybe, then a not yet. Technetium becomes a candidate, then an upper limit. Actinides remain intriguing but uncertain. The star does not become normal, but the mystery becomes better shaped. It is like watching a sculptor remove pieces of stone, not to destroy the statue, but to reveal what is actually there. For a sleepy mind, this may be one of the loveliest parts of the story. The universe is not only made of answers, it is made of careful almosts. A line almost matches, a model almost explains, an element almost seems present, a hypothesis almost works. Science moves through those almosts patiently, because rushing would only blur the view. Przybylski's star teaches that some mysteries are not solved by adding more excitement. They are approached by removing exaggeration, one uncertain line at a time, until the remaining strangeness is solid enough to stand on. So when you hear that radioactive elements have been reported in Przybylski's star, the best response is neither blind acceptance nor bored dismissal. It is curiosity with a steady hand. Some older studies argued for possible detections. Later studies questioned important ones. The evidence is tangled by the star's extreme line crowding. The atmosphere is undeniably bizarre. Short-lived elements, if confirmed, would require replenishment or production, but the confirmations are not secure enough to build the whole story on them. This is a mystery with guardrails, which is often the best kind, and behind those guardrails, the star keeps shining. It does not care whether we call a feature promethium or neodymium, technetium or a blend. The atoms absorb light according to their own rules. The magnetic field holds its quiet grip. The atmosphere remains layered, peculiar and difficult. Our task is not to make the star more dramatic than it is. Our task is to listen to the light until the drama that is truly there becomes clear. There is a special kind of stillness in Przybylski's star. and it may be one of the reasons the star can remain so strange. We have already met its unusual chemistry, the rare earth elements that speak too loudly in its spectrum, the iron that does not play the expected role, and the more delicate claims about radioactive elements that must be handled with care. But chemistry in a star does not happen in isolation. Atoms do not simply choose where to sit. They are pushed by light, pulled by gravity, stirred or not stirred by motion, and guided by magnetic fields. So if we want to understand why HD 101065 can wear such a peculiar chemical face, we need to look at the physical character of the star itself. And this is where another surprising fact appears. Przybylski's star is magnetic, and it may rotate so slowly that one full turn could take far longer than a human lifetime. That's a strange sentence, isn't it? We're used to thinking of stars as enormous, hot, active things. The sun turns once in roughly a month, depending on latitude, because its equator rotates faster than its poles. Many hotter stars rotate much faster than that. Some spin so quickly that their equators bulge outward, and their surfaces become distorted by their own motion. A star is not a solid ball like a painted globe on a desk. It is plasma, hot gas so energetic that electrons and nuclei move freely, and plasma often behaves with motion, flow, waves, and magnetic complexity. So when we hear about a star taking perhaps close to 2 centuries to rotate, the mind has to slow down with it. It is as if we are no longer watching a dancer, but a cathedral turning in space. The first clue that Przybylski's star turns slowly comes from its spectral lines. When a star rotates, one side of its visible disk moves slightly toward us while the other side moves away. The side moving toward us shifts its light very slightly toward shorter wavelengths, and the side moving away shifts its light toward longer wavelengths. When all that light is blended together, the star's spectral lines become broader. This is called rotational broadening. It is one of the ways astronomers estimate how fast a star is spinning, or at least how fast its equator appears to move across our line of sight. The measurement is called projected rotational velocity, usually written as V sin I, which is a compact way of saying, this is how fast the star appears to rotate, but we do not know the exact tilt of its axis. That little sin I matters. If a star is seen edge-on, its rotation is easier to measure because one limb is moving toward us and the other away from us as much as possible. If a star is seen almost pole-on, like looking down at the top of a spinning toy, the same rotation produces much less line broadening. So a small V sin I can mean the star truly rotates slowly, or it can mean we are looking nearly down its rotation pole, or some combination of both. Astronomy enjoys these little ambiguities. It never lets us have too much certainty without earning it first. For Przybylski's star, the lines are narrow. That suggests slow, apparent rotation. Not just a little slow, but slow enough that astronomers could examine subtle magnetic effects in certain lines. In earlier high-resolution studies, the spectral lines were measured to be narrow, with a very small projected rotational velocity. That already placed the star among the slow movers, at least from our viewpoint. But the story became even more interesting when researchers looked at its magnetic field over time. Magnetic stars have a useful habit. If their magnetic field is tilted relative to their rotation axis, then as the star turns, we see different magnetic hemispheres or different magnetic angles. The measured line of sight component of the field, called the longitudinal magnetic field, changes over the rotation cycle. Imagine a bar magnet inside a rotating star, though a real stellar magnetic field can be more complicated than a simple bar. As the star slowly turns, one magnetic pole may come more into view, then the other, or the field may shift from appearing more positive to more negative, depending on the geometry. By measuring that magnetic field again and again over years, astronomers can sometimes infer the rotation period. This is exactly the kind of long patience Przybylski's star demands. You cannot simply watch it for one night and see it turn. You cannot observe it for a week and mark the pattern. If the period is truly on the scale of many decades or centuries, then human observing campaigns capture only a piece of the cycle. It is like trying to understand the full motion of a clock by watching one slow movement of the hour hand. Except the clock is hundreds of light years away. The hand is magnetic, and the face is covered in rare Earth absorption lines. Still, astronomers are very good at patient measurement. They gather data across years, combine new observations with older ones, and look for trends. A 2018 study brought together magnetic field measurements spanning more than 4 decades and suggested that Przybylski's star may have a rotation period of about 188 years. That number is extraordinary. It would mean the star completes one turn in the time it takes human civilization to move from early photography to space telescopes, from handwritten observatory records to digital sky surveys, from gas lamps to smartphones that can accidentally ruin your night vision in one cheerful glow. If you were born on the star's surface, which would be inconvenient for many reasons, the landscape under the magnetic field would barely change over an ordinary human life. One stellar day would outlast generations. But we have to say this carefully. The 188-year period is not the same kind of measurement as timing a pulsation that repeats every few minutes. It is a probable interpretation of long-term magnetic variation, and the researchers themselves noted that it is not a unique solution and needs future verification. That caution matters. We are seeing only part of a very long cycle. There may be geometric effects, measurement differences between instruments, and complications caused by the star's abnormal atmosphere. A slow rotation period may be very likely, but the exact value is still something future astronomers will continue to test. Przybylski's star has a way of making even time feel peculiar. The magnetic field itself is central to the mystery. In magnetic AP stars, the field is often strong enough to influence the atmosphere profoundly. It does not have to be as extreme as a magnetar, this dead star monster whose magnetic field can distort atoms and shake space with bursts of radiation. Przybylski's star is not that kind of object. It is a living star, still shining by ordinary stellar power. But for a stellar atmosphere, a field of a few kilogauss can be very important. For comparison, Earth's magnetic field is less than 1 gauss at the surface, while a kilogauss is 1,000 gauss. So even a few kilogauss is not a small thing. It is strong enough to shape charged particles, influence line formation, and help keep the atmosphere stable. That stability is the key. In many stars, surface layers are mixed by convection or other motions. Material rises and sinks, smoothing out chemical differences. But in magnetic AP stars, the outer atmosphere can be relatively stable. The magnetic field suppresses some kinds of motion. The star may not have the same strong outer convection as cooler stars like the Sun. If the star is also rotating slowly, the atmosphere may remain undisturbed enough for atomic diffusion to work over long time scales. Radiation pushes some ions upward, gravity pulls others down. The magnetic field helps organize the whole process. Over time, certain elements gather in particular layers or regions while others become depleted. This is how a star can look chemically bizarre without needing to have been born from a wildly impossible cloud. Slow rotation strengthens this effect. A rapidly rotating star can develop circulation currents and mixing that interfere with delicate chemical separation. A slowly rotating star gives diffusion a quieter workshop. The atoms have time. The magnetic field has time. The atmosphere can sort itself into vertical layers and perhaps horizontal patches, chemical regions connected to the magnetic geometry. This is why the extreme slowness of Przybylski's star matters so much. It is not just a fun fact, although it is certainly the kind of fact one might gently bring up at a very patient dinner party. It may be part of the reason the star's spectrum is so strange. If the star has been turning almost motionlessly by stellar standards, then its atmosphere has had an unusually calm environment in which to develop chemical oddities. Picture the star not as a smooth glowing ball, but as a surface with invisible structure. Magnetic field lines emerge, curve, and re-enter. Chemical elements may be more abundant near certain magnetic regions. Some may gather high above the surface in thin layers, others may be concentrated lower down. As the star rotates, if it rotates at all noticeably, different chemical regions may gradually face Earth. In many AP stars, this causes periodic changes in brightness or spectral line strength. A patch rich in one element comes into view, then disappears. The star's spectrum changes with rotation. But if Przybylski's star rotates over nearly 2 centuries, those changes would unfold so slowly that a human astronomer might observe only a tiny portion of the cycle. The star's face would seem almost frozen. This slow magnetic face may also explain why the spectrum is so sharp and rich. Narrow lines are helpful because they reduce rotational smearing. If the star were spinning quickly, the lines would broaden and blend even more severely, making the already crowded rare earth forest harder to interpret. Slow rotation allows astronomers to see fine details. It does not make the spectrum easy, because nothing about HD 101065 seems eager to be easy, but it makes certain measurements possible. The narrowness of the lines lets researchers study magnetic broadening and line shapes, and it helps reveal the thousands of features that make the star's chemistry so extraordinary. There is a lovely contradiction here. The star is strange partly because it is so still, yet that stillness makes its strangeness easier to see. A fast-spinning version of Przybylski's star might blur its own fingerprints. This slow version holds them up line by line for astronomers to puzzle over. It is a cosmic riddle written in very fine handwriting, and the slow rotation keeps the page from being smeared. Magnetic fields also affect spectral lines directly. Through the Zeeman effect, a magnetic field can split a spectral line into multiple components. This happens because the magnetic field changes the energy levels of atoms or ions slightly, shifting the wavelengths they absorb or emit. In stars with strong enough fields and narrow enough lines, astronomers can sometimes see this splitting or measure its broadening effect. For Przybylski's star, certain rare earth lines, including lines from elements like gadolinium and samarium, have been used to estimate magnetic broadening. This is not a simple measurement, because the atmosphere is stratified and the lines are blended, but it gives evidence of a magnetic field strong enough to matter. The magnetic measurements can be complicated by the star's chemistry. In many stars, astronomers use a wide selection of lines to measure the magnetic field, but in Przybylski's star the line formation is unusual. Different elements may sit at different heights, and if the magnetic field changes with height, then lines from different elements might measure slightly different parts of the field. The 2018 study even discussed how anomalies related to vertical abundant stratification of praseodymium and neodymium can reveal a radial magnetic field gradient. That means the magnetic field strength or structure may vary with height in the atmosphere, and different rare earth ions may act like probes placed at different levels. This is wonderfully difficult. The same rare elements that make the spectrum confusing may also help map the magnetic structure. So the star is not only chemically stratified, it may be magnetically stratified in the observational sense as well. Lines forming high in the atmosphere may experience a different field strength than lines forming deeper down. The atmosphere becomes a layered laboratory. Neodymium and praseodymium are not just ingredients. They become markers of height, motion, and field. They are like tiny signposts suspended in a stellar atmosphere, though of course they are atoms, not helpful little signs saying, magnetic field stronger this way. Astronomy must infer the signs from the lines. This is one of the reasons Przybylski's star is so valuable, not just strange. It pushes models of magnetic stellar atmospheres. If astronomers can understand how its lines form, how its magnetic field varies, how its elements are layered, and how its slow rotation preserves these patterns, they can learn about the physics of chemically peculiar stars more broadly. Extreme objects are useful, because they show processes in exaggerated form. The Sun teaches us one kind of stellar physics, red giants teach another. White dwarfs, neutron stars, and magnetic AP stars each reveal different regimes. Przybylski's star is not only a curiosity, it is a stress test for stellar atmosphere theory. The slow rotation also raises a bigger question. How did the star become so slow? Stars are born from rotating clouds, and as material collapses inward, rotation can speed up, just as a spinning figure skater spins faster when pulling in their arms. Many young stars rotate quickly, though magnetic interactions with surrounding disks and stellar winds can remove angular momentum. For AP stars, the story of slow rotation is still studied. Some may lose angular momentum early in life through magnetic coupling with their birth environment. Others may be braked by magnetized winds. In the case of extremely slow rotators, the mechanisms must be efficient enough to produce periods of years, decades, or perhaps centuries. That is a remarkable outcome for a hot star, and it suggests a long history of magnetic influence. There is another possibility too related to viewing angle. As mentioned earlier, a very low projected rotational velocity could happen if we see the star nearly pole on. If the rotation axis points almost toward us, rotation produces little line broadening, but the long-term magnetic variations suggest that something more than viewing angle may be at work. The star's magnetic field appears to change slowly, and that kind of change fits a very long rotation period if the magnetic axis is tilted. Still, because the period is so long and the observations cover only part of it, astronomers remain cautious. A pole-on view, magnetic geometry, and true slow rotation all interact in the interpretation. The star keeps its secrets by mixing geometry with time. For bedtime purposes, though, the image is simple enough. Przybylski's star is not rushing. It may turn with almost unimaginable slowness. Its magnetic field steadies its atmosphere. Its chemical layers have time to form. Rare earth elements collect where starlight can reveal them. Iron peak elements appear weak. The whole visible surface becomes a quiet arrangement of physical effects working patiently together. Nothing about this needs to be frantic. The strangeness is not a storm. It is a long, slow sorting under magnetic control. This may be one of the most peaceful and unsettling things about the star. We often think mystery must be hidden in chaos, but here the mystery may be hidden in order. A stable magnetic field, a slow rotation, layers that persist, lines that remain narrow. The star is strange because it does not mix itself back into normality. It holds its peculiarities in place. The atmosphere has time to become a chemical display case, and the magnetic field is the quiet glass around it. There is a nice comparison with a spinning pot of soup, though perhaps not one a professional astrophysicist would lead with at a conference. If you stir a soup vigorously, the ingredients mix. Carrots, onions, herbs, and whatever else you have bravely included become distributed throughout. But if you leave a liquid undisturbed, layers can form, heavier bits sink, lighter materials rise, oils separate. Now imagine that, instead of a kitchen pot, we have a stellar atmosphere. Instead of spoons, we have radiation and gravity. Instead of a lid, we have a magnetic field. And instead of dinner, we have one of the strangest spectra in astronomy. It is not a perfect analogy, but it gives the right feeling. Stillness can separate what motion would mix. The star's slow turning may also affect how we experience its mystery across human time. A rapidly rotating variable star can reveal its pattern in a night or a week. Astronomers can watch its cycle, build a phase curve, and say, "Here is the period." Przybylski's star asks for patience across generations. If the 188-year period is close to correct, no single astronomer can observe a full rotation in a career. Understanding the whole cycle becomes a communal project, passed through records, instruments, and papers. Measurements made decades ago become precious. New observations do not replace old ones, they extend the timeline. The star's slowness turns astronomy into a relay race, with each generation carrying the magnetic curve a little farther. There is something deeply appropriate about that. A star that may take centuries to turn cannot be understood by impatience. It requires careful archives, repeated observations, and trust that future scientists will keep watching. This is science as long attention. Not one dazzling discovery, but a steady accumulation of evidence. Przybylski's star does not simply challenge our theories, it challenges our pace. And while this slow magnetic nature helps explain the chemical puzzle, it does not remove the wonder. In fact, it gives the wonder a physical foundation. We can say, perhaps the atmosphere is peculiar because the star rotates very slowly and has a magnetic field that allows diffusion and stratification to operate strongly. That sentence is sensible. It is also incomplete. How exactly are the elements distributed? Why are the rare earth enhancements so extreme? How do pulsations interact with the stratified layers? Hidden inside all that chemical stillness, there is a rhythm. That is one of the strangest things about Przybylski's star. A moment ago we were thinking of it as almost motionless, a magnetic star turning with such patience that one full rotation may take longer than a human lifetime. Its atmosphere seemed like a quiet display case, where rare earth elements could settle into strange layers, where magnetic fields could hold patterns in place, and where time itself seemed to move slowly enough for atoms to sort themselves into an extraordinary arrangement. But if astronomers listen in a different way, not to the slow turning of the star, but to the tiny changes in its light and spectral lines, HD101065 is not still at all. It is pulsing, quietly, quickly, and repeatedly, like a bell ringing deep inside a star that otherwise appears to be taking nearly 2 centuries to turn around. This is the next contrast that makes the star so fascinating. Przybylski's star may rotate with almost unbelievable slowness, yet it trembles on the scale of minutes. Its surface chemistry may be held in place by a stable magnetic field, yet its atmosphere also rises and falls with rapid oscillations. It is both patient and restless. If the slow rotation is the star's long breath, the pulsation is its heartbeat, and that heartbeat places it in a rare and important class of stars known as rapidly oscillating AP stars, or ROAP stars. The name is not exactly bedtime poetry, and it does sound a little like someone trying to say rope after being startled by a telescope, but the idea behind it is beautiful. These are chemically peculiar magnetic stars that pulse with short periods, usually just a few minutes to a little under half an hour. They are not exploding, they are not collapsing, they are ringing. A star can ring because it is not a rigid object. It is a sphere of gas and plasma held together by gravity, heated from within, structured by pressure, temperature, density, and sometimes magnetic fields. Disturb it in the right way, and waves can move through it. Some waves are shaped by pressure, rather like sound waves. Others can be shaped by buoyancy, gravity, rotation, or magnetic effects. In the case of rapidly oscillating AP stars, the pulsations are usually high overtone pressure modes. That sounds technical, but the basic picture is friendly enough. Pressure waves travel through the star and reflect inside it, setting up patterns of expansion and contraction. The star does not simply swell and shrink like a balloon in one simple motion. Instead, different layers and regions move according to standing wave patterns, a bit like the way a musical instrument can vibrate in different modes. This is why astronomers often compare stellar pulsations to sound. Not sound travelling through air to your ears, of course. Space between stars is far too empty for ordinary sound, and if Przybylski's star could make a noise, it would not arrive at Earth as a gentle hum. But inside the star, pressure waves behave in a sound-like way. They compress and expand the gas. They carry information about the interior. They make the starring at frequencies determined by its structure. In that sense, a pulsating star is like a musical instrument whose notes are set by gravity, temperature, density, and magnetism. The instrument is hundreds of light years away, slightly hotter than the Sun, chemically outrageous, and inconvenient to tune by hand, but the principle is there. The field of studying these stellar oscillations is called asteroseismology. It is the star version of seismology on Earth. Earthquakes send waves through our planet, and by studying those waves, scientists learn about layers deep underground. They infer the crust, mantle, outer core, and inner core because waves travel differently through different materials. Stars are not solid planets, but their pulsations also carry interior information. When a star brightens and dims rhythmically, or when its spectral lines shift back and forth because gas is moving toward and away from us, astronomers can use those changes to probe the star's inner structure. It is a remarkable idea. We cannot see inside the star directly, but we can learn from the way it vibrates. Przybylski's star holds a special place in this story because it was the first magnetic, chemically peculiar A-type star for which rapid oscillations were established. In 1978, its light was found to vary with a period of about 12.14 or 12.15 minutes. That means the star completes one pulsation cycle in about the time it might take you to make a cup of tea, let it cool slightly, forget where you put it, and then discover it again on the wrong side of the room. Every 12 minutes or so, a subtle rhythm passes through its visible layers. The change is small, far too small for the human eye to notice directly. To us, through an ordinary telescope, the star would still look like a faint point, but to precise instruments, the point is not constant. It flickers with structure. It breathes in a measured, repeating way. The amplitude of these changes is tiny, rapidly oscillating. AP stars do not generally pulse like large, dramatic variable stars whose brightness changes by huge amounts. They are more subtle. Their photometric variations can be measured in thousandths of a magnitude or less, depending on the star and observing method. In spectroscopy, the motion can appear as changes in radial velocity, with certain spectral lines shifting slightly as parts of the atmosphere move toward or away from us. This is where Przybylski's star becomes especially interesting, because not all lines behave in the same way. In ROAP stars, the rare Earth lines often show stronger pulsation signatures than lines from more ordinary elements. That is not an accident. It is a clue about where those elements sit in the atmosphere. Remember the layered atmosphere we have been building in our minds. Rare Earth elements such as praseodymium and neodymium may be concentrated high above the deeper layers where many iron peak lines form. If the pulsation wave grows stronger as it moves outward into the thinner upper atmosphere, then lines forming higher up can show larger velocity changes. In other words, the star's pulsation is not equally visible everywhere. The rare Earth elements may act like flags planted high in the atmosphere, waving more noticeably as the pulsation passes through. Iron lines lower down may remain quieter. So the same chemical peculiarity that makes the spectrum hard to interpret also makes the pulsations easier to study in certain lines. The star's weirdness becomes a diagnostic tool. That is one of the nicest turns in this story. Przybylski's star makes life difficult for astronomers, but it also gives them unusually sensitive markers. The rare Earth lines crowd the spectrum and complicate abundance measurements, yes. But because they form in unusual layers, they can reveal atmospheric motion and magnetic structure in ways more ordinary lines might not. Praseodymium and neodymium, the elements that help make the spectrum so strange, can also help trace the pulsation. They are not merely chemical oddities. They are instruments inside the starlight, showing how the upper atmosphere moves. The magnetic field shapes the pulsation too. In many ROAP stars, the pulsation axis is thought to be connected with the magnetic axis, rather than simply the rotation axis. This is part of what astronomers call the oblique pulsator model. The basic idea is that the star's pulsation pattern is aligned or strongly influenced by the magnetic field, and because the magnetic axis can be tilted relative to the rotation axis, the pulsations may appear differently as the star rotates. In stars with shorter rotation periods, this can cause the observed pulsation amplitude to vary over the rotation cycle. One side of the magnetic pulsation geometry faces us, then another, and the signal changes. For Przybylski's star, the rotation may be so slow that this modulation becomes almost glacial by human standards. If one rotation truly takes close to 2 centuries, then changes caused by the rotating magnetic geometry would unfold across decades. The star's rapid pulsation happens every 12 minutes, but the way we view that pulsation may shift only very slowly as the magnetic geometry turns. This is another wonderful contradiction. The pulse is fast. The viewing pattern may be slow. It's like listening to a bell that rings every few seconds, while the bell tower itself takes generations to rotate. The physics behind ROAP pulsations is still a field of active study. The basic cause is connected to pressure modes, but the exact driving and damping of the pulsations depends on the star's outer layers, magnetic field, chemical stratification, and convection. In many models, the hydrogen ionization zone plays an important role. This is a layer where hydrogen atoms are partly ionized, meaning electrons are being stripped from atoms and recombining in a way that affects how heat is trapped and released. A heat engine process can drive pulsations when energy is stored and released at the right phase of the cycle. But in magnetic AP stars, convection can be suppressed, and the magnetic field can modify how waves travel. So the simple picture becomes more complicated. The star is not just ringing because it was tapped. It is maintaining a self-excited oscillation through a delicate balance of energy, structure, and magnetic influence. One way to picture it is to imagine the star as a huge resonant body. Waves inside it can only fit in certain patterns, just as a guitar string vibrates at certain allowed notes, depending on its length, tension, and thickness. In a star, the string is the whole interior, and the allowed notes depend on the star's mass, radius, density profile, temperature structure, and magnetic field. Rapidly oscillating AP stars pulsate in high overtones, meaning the wave pattern has many radial nodes, many places where the motion changes direction, or passes through nearly no movement. The period is short because the waves are acoustic-like, and the relevant cavity inside the star supports rapid oscillations. For Przybylski's star, that roughly 12-minute rhythm is one of those allowed notes. This does not mean the whole star visibly expands and contracts in a simple way. The movement is subtle and structured. Some layers move more than others. Some chemical lines reveal the motion strongly because they form where the wave amplitude is high. The upper atmosphere may move back and forth with velocities that precise spectrographs can detect, while deeper layers show much smaller motion. That is why time-resolved spectroscopy is so valuable. Astronomers observe the star repeatedly over many short exposures, then measure how different lines shift with time. A rare Earth line might swing back and forth in velocity, another line might barely move. Comparing them reveals how the pulsation changes with height. In Przybylski's star, this vertical dimension is especially important because of the unusual atmospheric stratification. The rare Earth elements are not simply mixed evenly. They may be concentrated in high layers, and their lines can show different pulsation behavior from lines that form lower down. Some studies of ROAP stars show phase shifts between different spectral lines, meaning the pulsation wave reaches or affects different layers at different times. It's like watching ripples pass through a tall field of grass where the lower stems and upper tips do not move exactly together. The star's atmosphere is not a flat surface. It is a layered region where waves travel upward, reflect, steepen, and interact with magnetic fields. This gives astronomers a way to explore the atmosphere in 3 dimensions, though indirectly. A line from neodymium might tell them about one layer. A line from praseodymium might tell them about another. Hydrogen lines may form across a broader region. Iron lines may represent deeper layers. By comparing timing, amplitude, and velocity shifts, researchers can build a picture of how the pulsation behaves as it moves outward. This is not easy. The spectrum is crowded, the lines are blended, the magnetic field splits and broadens features, but the principle is powerful. The pulsation turns the star into a vibrating probe of itself. There is also a connection between the pulsation and the mystery of the magnetic field gradient. In some analyses, differences in how praseodymium and neodymium lines behave have been used to infer that the magnetic field may change with height in the atmosphere. That is a subtle idea. If different ions form at different atmospheric depths, and if their lines respond to different magnetic strengths, then their spectral behavior can reveal a vertical magnetic structure. The star is not only layered chemically, it may show a changing magnetic field through those layers. Again, the rare earth elements are not just confusing the spectrum, they are helping map it. One might ask why such a small pulsation matters when the star's chemical mystery is so large. The answer is that the pulsation gives motion to the mystery. Chemistry tells us what appears in the atmosphere. Magnetism tells us how the atmosphere may be held and shaped. Rotation tells us how slowly the surface patterns change. Pulsation tells us how the star's layers respond dynamically. It shows that the atmosphere is not a frozen shell. Even in a star that rotates with extreme slowness, waves are moving through the outer layers again and again. Every 12 minutes, the star performs a tiny experiment on itself, and astronomers can watch the spectral lines answer. This pulsing also helps place Przybylski's star in a wider family. It is not alone in being a rapidly oscillating AP star. Other ROAP stars have been found, many with magnetic fields, chemical peculiarities, rare earth anomalies, and short pulsation periods. Some have been discovered through photometry, others through high-resolution spectroscopy. Space telescopes and careful ground-based surveys have expanded the known sample. Each ROAP star gives astronomers another example of how magnetism, diffusion, and pulsation can coexist. But Przybylski's star remains special because its chemical peculiarity is so extreme, and because it was the prototype, one of the earliest and most important examples that showed this kind of rapid oscillation could occur in a magnetic AP star. There is a small historical sweetness in that. A star first famous for refusing to fit spectral categories later became central to a whole class of stellar pulsators. It was not merely odd in composition, it helped reveal a new kind of stellar behavior. The same object that confused abundance analysis also opened a doorway into magnetic astroseismology. That is often how unusual objects behave in science. At first, they are trouble. Then, if studied carefully enough, they become teachers. Przybylski's star has been both for a long time. For the listener, the 12-minute pulse offers a way to make the star feel less remote. 356 light-years is difficult to imagine. Rare earth stratification is difficult to picture. Magnetic line splitting and high overtone pressure modes are not exactly everyday thoughts, unless your everyday life is very specialized and possibly includes a spectrograph. But 12 minutes is familiar. 12 minutes is a kettle, a short walk, a pause before sleep, a few quiet breaths stretched into a small piece of evening. Somewhere in Centaurus, while you listen, Przybylski's star is likely completing pulse after pulse, not loudly, not visibly to the eye, but physically, rhythmically, measurably. Its atmosphere is moving in a tiny repeated pattern, while its rotation remains almost frozen. That makes the star feel oddly alive, though of course it is not alive in the biological sense. Stars do not think, choose, or feel, but they have cycles, they have rhythms, they have changing interiors and surfaces. A variable star is not a static lamp. It is a physical system in motion. Przybylski's star shines, pulses, slowly turns, holds chemical layers, and carries a magnetic field through space. All of this is governed by physics, but the combined effect is almost creature-like in the imagination. A slow, faint, chemically strange star with a rapid hidden heartbeat. The pulsation also reminds us that time inside a star can have many scales at once. Nuclear fusion in the core works over millions or billions of years. Atomic diffusion reshapes the atmosphere over long periods. Rotation may take decades or centuries. Pulsations repeat in minutes. Light crosses the distance to Earth in centuries. Human observations span decades. A single star contains all these clocks, and none of them cancel the others. Przybylski's star is not strange because it has one unusual timescale. It is strange because so many timescales overlap. The ancient life of a star, the slow patience of rotation, the subtle sorting of elements, the quick ringing of pressure waves, and the long delay of light reaching us. This is a useful thought as we continue. When we ask what explains Przybylski's star, there may not be one simple answer. Its chemical strangeness may come from diffusion. Its atmospheric stability may come from magnetism and slow rotation. Its pulsations may come from pressure modes shaped by magnetic fields and ionization layers. Its uncertain radioactive claims may involve blends, upper limits, or processes not fully understood. The star is a combination of effects, not a single trick. It is like a clock with many gears turning at different speeds, except one gear turns every 12 minutes, another perhaps every 188 years, and several gears are made of neodymium for reasons that require a paper to explain. As the pulse repeats, the mystery becomes richer rather than simpler. We can imagine the surface layers moving slightly outward and inward. Rare earth ions high in the atmosphere respond strongly. Spectral lines shift by tiny amounts. Instruments on Earth record the changes. Researchers fold the data over the pulsation period, compare phases, measure amplitudes, and try to connect the motion with the magnetic and chemical structure. A faint star becomes a laboratory for waves in a magnetized, stratified atmosphere. That is not merely a curiosity. It is physics under conditions no Earth laboratory can reproduce at stellar scale. The next time you think of a star as a point, it is worth remembering this. A point in the sky can be turning, pulsing, sorting atoms, bending spectral lines with magnetism, and sending out light that carries all of those details. The point is only small because we are far away. The reality is layered and active. Przybylski's star may look quiet through a telescope, but the quiet is deceptive. Inside its narrow spectral lines there is motion every 12 minutes, and this motion leads us toward the broader question that has been waiting behind all the details. If the star is magnetic, slowly rotating, chemically stratified, and rapidly pulsating, how much of its strangeness can be explained by known physics pushed to an extreme? How much remains uncertain because the spectrum is too crowded, the atmosphere too layered, or the data too incomplete? And where, if anywhere, do the more unusual ideas belong? What makes Przybylski's star so difficult is not that scientists have no ideas. They have many ideas, and that is almost the problem. Some of them are sensible and well-grounded. Some are cautious extensions of known physics. Some are much stranger, the kind that stand at the edge of the room wearing a serious expression and waiting for better evidence before being invited closer. The star is not a blank mystery. It is a crowded one. Its light gives astronomers too much to think about. Rare Earth elements in astonishing strength, iron peak elements that do not behave as expected, a magnetic field, very slow rotation, rapid pulsations, possible radioactive signatures that are hard to confirm, and a spectrum so full of overlapping lines that even identifying one element can feel like trying to hear a single whisper inside a library where every book is quietly reading itself aloud. So when we say astronomers still cannot fully explain Przybylski's star, we should not picture them staring at it with empty notebooks and shrugging helplessly. that would be unfair, and also a little dramatic, though astronomy has earned a little drama now and then. The real situation is subtler. Scientists understand parts of the puzzle. They can place the star in the family of magnetic chemically peculiar stars. They know it belongs among the rapidly oscillating AP stars. They have strong reasons to think that atomic diffusion, magnetic fields and atmospheric stratification are involved. They can model some of the rare earth enhancements. They can measure its pulsations. They can compare its spectrum with laboratory wavelengths. But when all of those pieces are placed together, the complete picture still does not settle into a neat, satisfying explanation. It is like assembling a jigsaw puzzle where many pieces are real, several are upside down, a few may belong to another box, and one corner appears to be made of promethium, which is inconvenient because promethium does not like to last. The most natural explanation begins with the kind of star it is. Przybylski's star is a magnetic chemically peculiar star, usually discussed as an AP star, though its exact spectral appearance has long been difficult because its chemistry is so unusual. In these stars, the atmosphere can be stable enough for atoms to separate. This is not ordinary mixing. It is sorting. Radiation from inside the star pushes some ions upward. Gravity pulls others downward. The magnetic field changes how charged particles move and suppresses certain kinds of turbulence. Over long periods, the atmosphere develops layers and patches. One element becomes concentrated in one region. Another sinks away. A third gathers high enough that its lines become strong in the spectrum. The visible surface becomes chemically selective, as if the star has been quietly arranging its atoms with tweezers. That idea explains a great deal. It can explain why a star's atmosphere might not represent the star's overall composition. It can explain why rare earth elements appear much more strongly than expected. It can explain why iron peak elements might seem weak in the visible layers, even if the star as a whole is not truly lacking iron. It can explain why a stable magnetic field and slow rotation would matter so much. If the surface layers are not constantly stirred, delicate separation can survive. A star that rotates quickly, mixes strongly, or churns like the sun's outer layers would smear out many of these chemical differences. Przybylski's star, with its narrow lines and possible century-scale rotation, seems to offer the opposite environment. Slow, stable, magnetic, patient. This is the best starting point because it uses known physics. Nothing supernatural is needed. No cosmic prankster has to sprinkle rare earth elements onto the surface. No hidden laboratory has to manufacture neodymium in the night. Atomic diffusion is real. Radiative levitation is real. Magnetic chemically peculiar stars are real. Other AP stars show unusual abundance patterns too. Przybylski's star is not alone in being chemically odd. It belongs to a known family. That is comforting, scientifically speaking. When an object can be placed in a family, even an eccentric family, it becomes less like a monster and more like an unusually complicated relative. But then comes the word extreme. Przybylski's star is not merely another member of the AP family with a few enhanced elements. Its rare earth spectrum is so intense that it stands out even among stars already labelled peculiar. Its lines from elements such as praseodymium, neodymium, holmium, and other lanthanides are unusually strong and numerous. Its spectrum is not just sprinkled with rare earth signatures, it is crowded by them. That creates the first major debate. Are the known diffusion processes enough to produce such extreme abundances in the visible atmosphere, or is something else needed? Can magnetic fields, slow rotation, and stratification fully account for the pattern, or do the models still fall short in important ways? This is where theory becomes hard. Atomic diffusion is simple in outline but very difficult in detail. Each element has many ionization states. Each ion absorbs radiation at specific wavelengths. The radiation field changes with height in the atmosphere. The atmosphere itself changes because those same elements absorb light and alter the temperature structure. The magnetic field affects motion. Pulsations affect velocity. Some layers may be stable, others less so. To build a full model, astronomers have to calculate how all these processes interact. That is not like making a grocery list. It is more like trying to predict where every dust mote in a sunbeam will be after a century, while the sunbeam changes because of the dust. A major natural explanation, then, is not a single sentence, but a whole system. Magnetic stabilization, slow rotation, radiative levitation, gravitational settling, vertical chemical stratification, possible horizontal abundance patches, and pulsation-modified line formation. That system can take us a long way. It lets the star stay inside physics. It lets the rare earth elements become visible through sorting rather than through impossible birth chemistry. It gives scientists a framework for why the spectrum is abnormal. But it does not automatically explain every observed line, every abundance value, or every controversial claim. It is the main road, but there are foggy turns along it. One of those foggy turns is the radioactive element question. This is the part that attracts the most attention because it sounds the strangest. Promethium, technetium, and some actinides have been discussed in connection with Przybylski's star. The reason this is so interesting is that promethium and technetium have no stable isotopes. They decay. If they were truly present in the atmosphere in measurable amounts, they would need to be made recently, supplied recently, or continuously replenished. Otherwise, over the long life of the star, they would disappear. This would be like finding fresh footprints in a sealed ancient room. Either someone has been inside recently, or the marks are not what they first appear to be. Older studies suggested possible detections of promethium and technetium in the spectrum. Some studies also explored possible actinide signatures. But the newer and more cautious view is that the evidence for some of these elements is not secure. The star's spectrum is heavily blended. A candidate line of promethium can overlap with lines from other neutron capture elements. A possible technetium line can sit inside a complex blend. When researchers synthesize the spectrum using known lines from many elements, some of the dramatic candidates become less convincing. For promethium, newer work concluded that it is not currently possible to definitely claim its presence in the atmosphere. For technetium, newer work reduced the claim to an upper limit rather than a firm detection. In less technical language, the data do not force astronomers to say, yes, it is there. That caution matters because the radioactive elements would change the story dramatically. If short-lived elements were confirmed, ordinary diffusion alone would not be enough. Diffusion can sort atoms that are already present, but it does not create unstable nuclei out of nothing. A real detection of short-lived radioactive elements would require a source. Scientists have considered several possibilities. One is surface irradiation by neutrons, where free neutrons strike seed nuclei and build heavier radioactive elements. Another is photonuclear reactions, where high-energy gamma rays interact with nuclei. Another is a hidden compact companion, perhaps a neutron star, providing energetic particles or radiation. These are fascinating ideas. They are also demanding ideas. They require evidence, mechanisms, and consistency with what is observed. The neutron star companion idea is especially strange. A neutron star is the collapsed core of a massive dead star, incredibly dense, with strong gravity and often intense magnetic fields. If Przybylski's star had such a companion, perhaps that companion could provide a source of high-energy particles or radiation capable of altering the star's atmosphere. It sounds like the beginning of a cosmic detective story. A quiet, chemically peculiar star, and somewhere nearby, a hidden dead star quietly influencing its surface. But evidence for such a companion is not established. A good scientific explanation cannot simply be exciting. It has to match observations. It must account for the star's motion, brightness, spectra, possible companions, and lack of certain expected signatures. Without that, the neutron star idea remains speculative, interesting but not settled. Another strange idea involves long-lived super-heavy elements. Perhaps, some researchers have suggested, the star contains heavy nuclei that decay into lighter radioactive products. If extremely long-lived super-heavy nuclei existed in the atmosphere, their decay might produce some of the unusual species seen or suspected. This idea is intriguing because it connects Przybylski's star with nuclear physics beyond the usual stable elements. But it also faces serious challenges. Super-heavy elements are difficult to produce and generally very unstable in laboratory settings, though nuclear theory allows for the possibility of islands of relative stability. Whether such elements could exist in a star's atmosphere in meaningful amounts, survive long enough, and produce the observed line pattern is far from established. It is the kind of idea that makes the imagination sit up, but science asks it to bring identification papers, laboratory wavelengths, abundance consistency, and a plausible formation history. External pollution is another possibility. Could the star have accreted unusual material from outside? Stars can gather material from their surroundings, from a companion, or from debris. In some cases, surface abundances can be changed by accretion. Perhaps processed material rich in unusual elements landed on the star's surface. But this explanation also has problems. The abundance pattern in Przybylski's star is not simply extra heavy elements everywhere. It is selective, stratified, magnetic, and tied to the peculiar atmosphere. Accretion might contribute in some scenario, but it does not automatically produce the rare earth dominance, weak ion peak appearance, slow rotation, ROAP pulsations, and layered line formation all at once. A sprinkle of exotic material does not by itself explain the whole recipe. A more grounded possibility is that Przybylski's star is an extreme example of known app-star physics, not a separate category. In this view, the star is not asking for a new source of elements. It is asking for better models of diffusion, magnetism, and stratification. The rare earth elements may be concentrated so strongly in the upper atmosphere that they mimic impossible abundances. The weak ion lines may reflect where iron sits, rather than how much iron the star contains overall. The possible radioactive detections may mostly be blends. The unusual pulsation behavior may help reveal the layered atmosphere rather than requiring exotic nuclear processes. This is the conservative view, and conservative does not mean boring. It means starting with the simplest physics that can explain the most facts. But even this conservative view still leaves questions. Why is this star so extreme compared with other chemically peculiar stars? What initial conditions made it this way? Did its magnetic field form unusually strong or stable? Did it lose angular momentum early, allowing such slow rotation? Is its atmosphere especially calm? Are its pulsations interacting with the stratification in a way that enhances certain lines? Are we seeing it from a particular angle that makes the chemistry look even more unusual? How much of the spectrum has been misread because the line lists are incomplete or the blends are too complex? These are not small questions. They are the reason the star remains a living problem rather than a solved curiosity. The viewing angle may sound like a minor detail, but it can matter. If the star's magnetic axis and rotation axis are arranged in a certain way relative to Earth, we may see particular chemical regions more strongly. In many AP stars, elements are not spread evenly across the surface. They can form spots or belts related to the magnetic field. As the star rotates, those regions come into and out of view, changing the spectrum. But if Przybylski's star rotates extremely slowly, we may have been seeing nearly the same hemisphere for the entire period of detailed observation. That means our picture of the star may be incomplete. We might not yet know how its spectrum changes over a full rotation. If one turn takes close to 2 centuries, astronomers have only watched part of its face. That is a wonderful and slightly frustrating thought. A star can be studied for decades and still not have shown us all sides. Human time is short. Stellar rotation can be long. A child born when some of the earlier magnetic measurements were made could grow old before enough of the cycle passes to confirm the full pattern. Future astronomers may inherit this question from the present. They may compare their measurements with those made generations earlier and slowly refine the period. Przybylski's star forces science to become patient. It does not reveal its rotation schedule quickly, and there is no polite way to hurry a star. The pulsations add another layer to the debate. Rapidly oscillating, AP stars are valuable because their pulsations probe their interiors and atmospheres. In Przybylski's star, the pulsations are strongly visible in some rare Earth lines, suggesting that those lines form high in the atmosphere where the pulsation amplitude is large. This helps confirm the idea of vertical stratification, but it also complicates abundance analysis. If different lines form in different layers that are moving differently, then a simple static model may not capture the full behavior. The atmosphere is not just layered, it is vibrating. It is magnetic, chemically peculiar, slowly rotating, and pulsing. A model that ignores any of those pieces may explain one part while failing another. Line blending remains one of the most practical obstacles. It sounds mundane compared with hidden neutron stars or super-heavy elements, but it may be the most important debate of all. Many controversies in Przybylski's star come down to whether a particular absorption feature really belongs to a particular element. In a cleaner spectrum, this would be easier. In HD 101065, rare Earth lines are everywhere. The line lists are long, complex, and not perfect. Some atomic data may be uncertain. The spectrum contains features from many ionization states. Magnetic splitting and pulsation can change line shapes. So acclaimed detection must survive a difficult test. Not just, is there a feature at this wavelength, but can every more likely blend be ruled out, and does the required abundance make sense across multiple lines? That is a high bar, as it should be. This is why newer studies revisiting promethium and technetium are so valuable. They do not make the star ordinary by questioning old claims. They improve the boundary between what is known and what is possible. They say, in effect, here is what the evidence can support and here is where it cannot yet go. That kind of work may seem less glamorous than announcing an impossible element, but it is the work that keeps astronomy honest. A mystery does not need every rumour to remain mysterious. Przybylski's star still has enough confirmed strangeness to fill the room. The debates also show how science changes over time. Early observations revealed the star's peculiarity. Later, high-resolution spectra revealed more detail. Improved atomic data allowed better line identifications. Space-based astrometry refined distance and motion. Magnetic measurements over decades suggested extremely slow rotation. New analyses revisited radioactive claims with more complete line lists and synthetic spectra. At each stage, the star was not simply explained or unexplained. It was explained a little better, and the remaining uncertainty became more specific. That is how real science often progresses, not from darkness to sudden daylight, but from blur to sharper blur, and then slowly to structure. For the listener, perhaps the easiest way to hold the debate is this. The star has a strong natural explanation for much of its weirdness. It is a magnetic, slowly rotating, chemically peculiar star whose atmosphere has been sorted by atomic diffusion. That is the main foundation. Around that foundation are unresolved details, the extreme size of the rare earth enhancements, the weakness of iron peak features, the exact atmospheric stratification, the full magnetic geometry, the true rotation period, and the role of pulsations. Beyond those are more speculative ideas. Radioactive elements, surface irradiation, hidden companions, super-heavy nuclei, or other processes that may or may not be needed. The mystery is layered, just like the atmosphere. There is a gentle lesson in that layering. The most exciting explanation is not always the best one. The simplest explanation is not always complete. The careful answer often sits between them. Przybylski's star may not require aliens, hidden laboratories, or impossible physics. It may be nature being subtle in a way our models have not fully captured, but it also cannot be brushed aside as just another chemically peculiar star, because its spectrum remains extreme, its reported anomalies have a long history, and its combination of properties is rare. It asks for humility from both sides, from those who want to make it sensational, and from those who want to make it ordinary too quickly. And yes, there have been artificial explanations suggested in popular discussion, because whenever a star is strange enough, the idea tends to appear. Perhaps an advanced civilization did something. Perhaps the odd elements are a sign of technology. Perhaps the spectrum is not natural. These ideas make good conversation, especially late at night when the universe feels large and the imagination has had too much tea. But scientifically, there is no need to reach for them first. Natural mechanisms already explain many features, and the remaining uncertainties are not evidence of engineering. A gap in understanding is not a signature of intelligence, it is a gap in understanding. That may sound less thrilling, but it is much safer, and in this case still wonderfully strange. Przybylski's star is mysterious enough without turning it into a message. It is a star whose atmosphere may be one of the strangest chemical sorting experiments in the galaxy. It is a star where rare earth ions rise into view, where magnetic fields hold structure, where rotation may be almost impossibly slow, where pulsations ring every 12 minutes, and where spectral lines are so crowded that even radioactive claims become difficult to confirm or dismiss completely. That is plenty. The natural universe does not need help being astonishing. It has been astonishing quite effectively for about 13 billion years. What scientists still debate then is not whether the star is strange. That is settled. The debate is how the strangeness is produced, how far known physics can be pushed, and which of the more exotic claims survive careful scrutiny. They debate the exact abundance pattern. They debate line identifications. They debate whether some candidate radioactive features are real or blended. They debate the details of magnetic field structure. They debate how diffusion works in such an extreme atmosphere. They debate the rotation period, and whether future observations will confirm the long magnetic cycle. They debate whether any additional process is needed beyond the AP star framework. This kind of debate is not a weakness in science. It is the sound science makes when it is working properly. The data are difficult, the object is unusual, the models are incomplete, so scientists test, revise, argue politely in papers, and sometimes less politely in conference coffee lines, though one hopes with good biscuits nearby. Over time, weak claims fall away. Strong claims remain. New measurements sharpen the picture. The star becomes not less mysterious necessarily, but more accurately mysterious. That phrase may be the best way to leave this part of the journey. Accurately mysterious. Przybylski's star is not a vague oddity. It is a measured one. Its coordinates are known. Its light has been studied. Its rare earth excesses are real. Its magnetic nature is real. Its rapid pulsations are real. Its possible radioactive signatures are debated. Its slow rotation is probable, but still awaiting the long patience of future confirmation. The mystery is not a fog with no shape. It has edges, layers, and named uncertainties. At the edge of explanation, this small star becomes more than a puzzle about chemistry. It becomes a reminder of how science really works when the universe is not in a hurry to be understood. Przybylski's star is not the kind of mystery that sits in total darkness giving us nothing, it gives us plenty. It gives us light, spectra, pulsations, magnetic measurements, rare earth lines, possible long-term rotation changes, and decades of careful observations. It gives so much, in fact, that the difficulty is not silence, but interpretation. The star is speaking in light, but it speaks in a crowded language, full of overlapping signatures, rare elements, uncertain line identifications, and physical processes that do not arrange themselves neatly for our convenience. And perhaps that is the first lesson it teaches us. Not every mystery is mysterious because we lack evidence. Some mysteries remain because the evidence is rich, tangled, and asking us to become better readers. This is easy to forget because from Earth the star looks so modest. A faint point in Centaurus, not bright enough to be seen with the unaided eye, not famous in the way Sirius is famous, or Betelgeuse or Alpha Centauri, the nearby celebrity of that same southern region. Przybylski's star does not command the sky by brightness. It earns attention by detail. It waits until astronomers split its light into a spectrum, and only then does the ordinary point become extraordinary. That alone is a lesson about appearances. The universe hides some of its most interesting information not in the obvious glow, but in the fine print. A star can look quiet and still carry a chemical riddle that lasts for generations. A tiny line in a spectrum can be more important than 1,000 casual glances. In a way, HD 101065 is a test of patience. It asks astronomers to slow down and sort the certain from the uncertain. The certain things are already remarkable. It is a chemically peculiar magnetic star. It belongs to the rapidly oscillating AP family. Its atmosphere shows extraordinary rare Earth signatures, with elements like neodymium, praseodymium, holmium, and others appearing far more strongly than they do in ordinary stellar spectra. Its iron peak elements do not behave in the expected way. Its magnetic field helps shape a stable atmosphere. Its pulsations repeat on the scale of minutes, even while its rotation may be so slow that one full turn could take many decades or perhaps nearly 2 centuries. These facts do not require exaggeration. They already show us a star operating in a rare and extreme corner of stellar physics. The uncertain things are just as important, because they show where knowledge has edges. Some of the more dramatic claims around Przybylski's star involve radioactive elements: promethium, technetium, actinides, names that sound like they belong to deep nuclear laboratories rather than a quiet star in Centaurus. Older studies and discussions explored possible signatures of these unstable elements, and if they were confirmed clearly, they would demand some kind of ongoing production, replenishment, or unusual process. But later, more cautious work has shown how difficult these claims are. Many possible lines are blended with other heavy element signatures. A feature that looks tempting can be partly or entirely explained by something else. The star's rare Earth spectrum is so crowded that certainty becomes hard-won. So the honest answer is not simply, yes, impossible elements are there, and not simply, no, nothing unusual is happening. The honest answer is quieter and more careful. Some claims remain uncertain. Some have weakened. The confirmed strangeness remains. The debate continues. That may sound unsatisfying if we want a clean ending, but it is deeply satisfying if we want truth. Science does not become stronger by pretending uncertainty has vanished. It becomes stronger by naming uncertainty accurately. Przybylski's star teaches that there is a difference between not knowing and knowing nothing. We do know a great deal. We know enough to say it is one of the most peculiar stellar atmospheres ever studied. We know enough to place it in a real physical framework. We know that magnetic fields, atomic diffusion, and atmospheric stratification probably explain much of the odd chemistry. But we do not yet know every detail of how those processes combine to produce such an extreme spectrum. We do not know exactly how all the disputed line identifications should be resolved. We do not yet know, with perfect confidence, the full rotation cycle of the star. We do not know whether every unusual feature can be explained by ordinary apstar physics pushed to its limit, or whether some additional process is needed. There is humility in that, and humility is one of the most useful tools in science, even though it does not fit neatly into a telescope dome. A telescope can collect light. A spectrograph can separate wavelengths. A computer can model atmospheres. A laboratory can measure atomic transitions. But humility is what keeps us from forcing the star to be simpler than it is. Humility lets astronomers say, this line might be Promethium, but it might be blended. It lets them say, this rotation period is probable, but not unique. It lets them say, this model explains many features, but not all. That kind of honesty may not sound dramatic, yet it is what makes scientific mystery different from fantasy. It does not remove wonder, it protects it. Think about the path we've taken through this star. We began with a faint point in the southern sky, ordinary to the eye and extraordinary to the instrument. We followed Antoni Przybylski's recognition that its spectrum did not fit the old expectations. We opened that spectrum and found the strange fingerprints of rare earth elements, a forest of lines where the usual chemical balance seemed rearranged. We considered the careful mystery of radioactive elements that should not last, learning that the most exciting claims must pass through the narrow doorway of evidence. We watched the star turn, perhaps with astonishing slowness, under the grip of a magnetic field. We listened for its rapid pulse, that 12-minute rhythm inside a star that may take generations to rotate. And then we gathered the explanations, from the grounded to the speculative, seeing how much known physics can do and how much remains unsettled. The result is not a single answer, but a better question. What kind of atmosphere can make a star look like this? That question reaches into many parts of physics. It asks about atomic diffusion, the slow sorting of elements under gravity and radiation. It asks about radiative levitation, where starlight itself can push certain ions upward. It asks about magnetic fields, which can stabilize the atmosphere and guide charged particles. It asks about rotation, because a star that barely turns may allow chemical patterns to persist for astonishing lengths of time. It asks about pulsation, because the star's outer layers do not merely sit there, they ring. And it asks about spectroscopy, because the entire mystery is known through light separated into lines. There is something very beautiful about that. Przybylski's star teaches us that knowing the universe often means learning to trust indirect clues. We cannot touch the star. We cannot scoop material from its atmosphere. We cannot stand nearby and take a sample, which is for the best, since standing nearby a star tends to be a short and poorly reviewed experience. Instead, we receive light. That light has travelled for centuries. It enters our instruments as a faint signal. Then, through physics, patience, and comparison with atoms studied on Earth, it becomes a story about a distant atmosphere. Astronomy is a science of distance overcome by inference. It is the art of learning from what arrives, and yet inference has limits. That is another lesson. A spectrum is powerful but not magical. When lines overlap, certainty becomes difficult. When atomic data are incomplete, identifications become uncertain. When a star's atmosphere is stratified, a simple abundance number may hide layers of complexity. When magnetic fields split lines and pulsations shift them, and rare earth ions crowd the wavelength range, the interpretation becomes even more delicate. A star does not have to hide behind dust to be hard to understand. It can hide inside too much detail. This is why Przybylski's star is not only a strange object, but a kind of mirror. It shows us the limits of our models, not the failure of science, but the places where science needs to grow. Models are not reality itself. They are tools. Good tools, powerful tools, astonishing tools, but tools all the same. A model atmosphere can predict how light should move through gas under certain assumptions. But if the real atmosphere is layered, magnetic, pulsating, and chemically extreme, then the model must become more sophisticated. The star is not wrong for refusing to match the model. The model is incomplete if it cannot match the star. That is how nature teaches us. It does not give lectures. It gives mismatches. Those mismatches have always driven science forward. Mercury's orbit did not quite fit Newtonian predictions, and that small mismatch helped point toward general relativity. The ultraviolet catastrophe in blackbody radiation helped open the door to quantum mechanics. the strange spectra of stars helped reveal the composition of the universe. Pulsars, quasars, dark matter, dark energy, gravitational waves, exoplanets. All of these entered science because something did not look quite right under the old view. Przybylski's star belongs to that tradition on a smaller, quieter scale. It may not rewrite all of physics, but it does press on the boundaries of stellar atmosphere theory. It asks us to refine the way we understand magnetic stars, chemical separation, rare earth line formation, and the careful identification of elements under difficult conditions. There is comfort in that. A mystery does not have to be cosmic in size to be meaningful. It can be one faint star, one difficult spectrum, one stubborn atmosphere. The universe is not only mysterious at the larger scales, in black holes, cosmic expansion, dark matter, and the beginning of time. It is also mysterious in the details, in the way an atom absorbs light, in the way a magnetic field keeps a stellar atmosphere calm, in the way a rare earth element rises into visibility, in the way a line that might belong to one element turns out to be blended with another. The small mysteries are not lesser, they are the texture of reality. Przybylski's star also teaches us about the danger of wanting the strangest answer too quickly. When we meet something unusual, the imagination naturally runs ahead. Could it be radioactive? Could it be artificial? Could it be a sign of something entirely unknown? Those questions are not shameful. Curiosity often begins by wondering, but science then asks curiosity to sit down, take notes, and check the evidence. The star may inspire strange ideas, and some strange ideas are worth testing. But the strongest explanation is not the one that sounds most exciting. It is the one that explains the most evidence with the fewest unsupported assumptions. In this case, the natural physics of magnetic AP stars explains much of the puzzle, even if it does not yet explain everything. That is not disappointing. It is a reminder that nature's ordinary laws, operating under unusual conditions, can produce results that feel almost impossible. It is also worth remembering that unexplained does not mean unexplainable. There is a difference. An unexplained thing is something we have not fully understood yet. An unexplainable thing would be something forever beyond reason. Przybylski's star does not ask us to abandon reason. It asks us to sharpen it. It asks for better spectra, better atomic data, better magnetic models, longer time baselines, and more careful comparisons. Future astronomers may resolve some of today's uncertainties. They may confirm or reject the long rotation period more confidently. They may refine the abundance pattern. They may settle more of the radioactive element claims. They may build models that show exactly how such an extreme atmosphere can form. The star may someday become less mysterious, but even then, it will have done its work. It will have forced science to become more precise. There is a gentle human lesson in that too. We live surrounded by things we do not fully understand. Some are cosmic, like the chemistry of a distant star. Some are personal, like memory, time, grief, love, and why a sock can vanish from the laundry with such impressive consistency. Not knowing can feel uncomfortable, but it can also be spacious. It gives the mind room to wonder. The important thing is how we treat the unknown. We can fill it too quickly with certainty, or we can approach it with patience. Przybylski's star rewards the second approach. It is a star for patient minds, and maybe that is why it fits so well into a quiet journey like this. It is not a supernova blasting itself apart. It is not a black hole tearing matter into light. It is not a planet raining iron, or a galaxy colliding in a storm of stars. It is quieter than that. A faint point, a strange spectrum, a slow turn, a quick pulse, a puzzle held in starlight. Its drama is not in violence, but in difficulty. It shows that the universe does not always need to shout to be profound. Sometimes it only needs to place the wrong element in the wrong strength at the wrong wavelength and wait for someone to notice. As we step back from HD 101065, the star remains where it has always been, shining in Centaurus, sending its light outward in every direction. Somewhere in that light are the marks of rare Earth elements, the signs of magnetism, the subtle motion of pulsation, and perhaps still a few disputed clues that future studies will examine with better tools. The star is not waiting for us exactly. It has no concern for our confusion. But we are waiting on it, in a way. Waiting for longer measurements, waiting for sharper spectra, waiting for better models, waiting for the slow rotation to reveal more of its face. Science for this star has to move at a pace the star allows. So perhaps the final lesson is this. The limits of knowing are not walls, they are horizons. You can move toward them, you can measure more carefully, you can build better instruments. You can learn new physics, revise old assumptions, and clear away mistakes, but each horizon reached may reveal another one beyond it. That is not failure. That is the shape of discovery. Przybylski's star sits at one of those horizons, small and faint and deeply strange, showing us that even in a galaxy filled with hundreds of billions of stars, one quiet point of light can still make human knowledge pause. And now, as our thoughts begin to settle back from Centaurus, we can leave the star with its mystery intact. Not solved completely, not made ordinary, not inflated beyond the evidence, but appreciated for what it truly is. A real object in the sky that has challenged astronomers for more than half a century. A magnetic, pulsing, chemically peculiar star whose light carries some of the strangest fingerprints we have ever read. If you are listening late at night, perhaps somewhere under your own small sky, it is comforting to remember that the universe still contains things no one fully understands. Not because understanding is impossible, but because reality is deep. There is always another layer in the light. And if this quiet journey through Przybylski's star has brought you a little calm, a little curiosity, or simply a soft place for the mind to rest, I would be grateful if you liked the video, subscribed, and shared this sleepy corner of science with someone else who enjoys a mystery that does not rush. Somewhere far away, in the southern sky, HD 101065 keeps shining. Its rare elements keep marking the light. Its magnetic field keeps holding the atmosphere in a strange arrangement. Its hidden pulse keeps beating every few minutes, tiny and steady across the centuries, and here, for a little while, we have listened. Sleep well, fellow traveller, wherever you are beneath the turning earth. The star nobody can fully explain is still out there, faint and patient, reminding us that not knowing is not the end of wonder. Sometimes it is where wonder begins.